The detection comes first as numbers, a sequence of coordinates logged by automated survey telescopes, scanning the same patches of sky night after night, looking for anything that moves against the fixed stars. Most objects drift in predictable arcs, asteroids in their elliptical rounds, comets returning on schedules written millions of years ago. But this one moves differently. The trajectory analysis flags it immediately. Eccentricity greater than unity. Velocity too high. Angle wrong. Something from elsewhere, passing through. They designate it 3I Atlas, the third interstellar object formally catalogued, discovered by the Asteroid Terrestrial Impact Last Alert System in Hawaii, a network built to watch for dangerous rocks, now catching glimpses of what wanders between stars. The I stands for interstellar, a category that did not exist in astronomical nomenclature until 2017, when Oumuamua taught us that such visitors arrive more often than we thought. Before that first confirmed detection, interstellar objects were theoretical, predicted by models of planetary formation, expected to exist in vast numbers drifting through the galaxy, but never seen. Now we know to look for them. Now we catalogue their passage. 3I Atlas appears first as a faint smudge of light, magnitude 20 or fainter, requiring large telescopes and long exposures to register at all. At discovery, it lies perhaps 6 or 7 astronomical units from the Sun, somewhere between Jupiter and Saturn, already well inside the orbits of the gas giants, already committed to its hyperbolic path. The initial observations reveal motion of several arc-seconds per hour against background stars. Fast enough to be obvious in successive images, slow enough to track with precision. Astronomers calculate backward, tracing where it came from. The trajectory points toward a region of sky in the constellation Lyra, toward no particular star, from the general direction of the galaxy's rotation. It has travelled for millennia to reach this moment of detection, moving perhaps 20 or 30 kilometers per second relative to the local standard of rest, roughly the speed at which the Sun itself orbits the galactic centre. No one knows what sent it on this path. Gravitational perturbation from a passing star, perhaps billions of years ago, when the object still orbited some distant sun, or ejection during planetary formation, flung out by the chaotic gravitational dance of giant worlds coalescing from protoplanetary disks. Most comets in our own solar system's Oort cloud sit barely bound to the Sun, their orbits so vast and tenuous that a slight nudge from a neighbouring star or a passing molecular cloud can send them either inward toward the inner planets or outward into interstellar space entirely. Every planetary system likely produces exiles objects accelerated past escape velocity, set adrift. The galaxy fills slowly with these wanderers, a diffuse population of ice and rock moving between the stars at speeds measured in kilometers per second, taking millions of years to cross the distance between neighbouring star systems. 3I Atlas carries no record of its origin. No isotopic signature identifies which stellar nursery forged its ice. No orbital history survives the gravitational chaos that set it free. It enters our solar system as pure present tense, a visitor defined only by where it is now, where it has been for the last few thousand years of travel, where it will go next. Only took a few million years to get here, travelling blind through the dark, hitting this particular system by pure geometric chance. The probability of any single interstellar object passing through our solar neighbourhood in human observable proximity is infinitesimal. The probability of at least one doing so in any given year, considering the vast numbers drifting through the galaxy, becomes statistically inevitable. We simply had to watch long enough, carefully enough, with sensitive enough instruments. The early observations focus on establishing the orbit with confidence. Each night of clear weather, telescopes return to the object's predicted position, capturing its location against background stars with sub-arc second precision. The orbital elements refine with each measurement. Eccentricity approximately 1.03, give or take a few hundredths, depending on how outgassing affects the trajectory. Inclination, roughly 60 degrees to the ecliptic plane, coming in at an angle that crosses through the planetary orbits rather than moving along them. Perihelion distance perhaps 0.5 astronomical units, maybe less close enough that the sun's heat will drive significant activity from the surface, if there is surface ice to drive it. The uncertainty in these numbers narrows day by day, observation by observation, as the orbital arc lengthens and the mathematics grow more confident. Somewhere in the data, a mystery persists quietly. The absolute magnitude, the intrinsic brightness of the object, corrected for distance and illumination angle, suggests something relatively small, perhaps a few hundred meters across, perhaps a kilometer. Difficult to say without knowing the albedo, the reflectivity of the surface. Dark objects appear fainter for their size. Icy objects shine brighter. The spectrum will tell more, once there is enough light to spread into wavelengths. For now, it remains a point source, a mathematical abstraction moving through space at velocities that will carry it back out past Neptune within a year or two of perihelion. Gone from easy observation, continuing outward on a path that will never close. Only took 4.5 billion years for our solar system to receive this particular visitor, arriving now, in this moment, when humans happen to be watching with digital sensors and orbital mechanics software and international networks of telescopes. A century ago, it would have passed unnoticed, too faint for photographic plates, unless someone aimed a large telescope at precisely the right patch of sky on precisely the right night. A century hence, it will be far beyond Neptune, fading into the darkness between worlds, still moving, still following the hyperbolic curve imprinted by the sun's gravity, unreachable by any probe we might conceivably build and launch in time to catch it. The designation settles into databases. Orbital elements populate prediction tables. Ephemerides list its future positions for observers worldwide. And 3i Atlas continues inward, warming slowly, falling toward the star that will bend its path and send it away forever, unaware that it has been noticed, unaware that it carries anything unusual, simply existing in the present tense of motion through vacuum, as it has existed for longer than our species has walked upright, as it will exist long after we are gone. The mathematics describe a curve that does not return. In orbital mechanics, eccentricity measures the shape of a path 0 for a perfect circle, values between 0 and 1 for ellipses of increasing elongation, exactly 1 for a parabola that escapes to infinity at 0 velocity, and greater than 1 for hyperbolas that retain excess speed even at infinite distance. 3i Atlas moves on a hyperbola. The sun's gravity bends its trajectory, curves it inward and then back outward, but cannot capture it. The object carries too much kinetic energy relative to the sun's gravitational potential at this distance. It will leave faster than it arrived, accelerated by the gravitational assist of its close passage, but it will leave nonetheless. The equations are elegant in their simplicity. Vis viva equation. Conservation of energy. Kepler's laws extended to unbound orbits, all the same mathematics that govern planets and moons and asteroids, merely applied to trajectories where total orbital energy is positive rather than negative. For bound orbits, the sum of kinetic and potential energy stays negative, trapping the object in eternal return. For unbound orbits, the sum is positive or 0, and the object escapes. The difference between captivity and freedom, astronomically speaking, reduces to a single numbers sign. Observers calculate the orbital elements with increasing precision as more data accumulates. Semi-major axis negative, which seems paradoxical until one remembers that for hyperbolic orbits. The semi-major axis is defined as a mathematical convenience, a value that makes the equations work but doesn't correspond to any physical dimension of the path. Perihelion distance 0, 47 astronomical units, roughly halfway between the Sun and Earth's orbit, close enough that surface temperatures at closest approach will rise to several hundred Kelvin, warm enough to sublimate water ice vigorously, warm enough to drive carbon monoxide and carbon dioxide into the coma if those volatiles exist in the nucleus. The perihelion date itself remains uncertain to within a day or two at this early stage, sometime in mid-passage through the inner system. A moment when the object will be moving at maximum velocity relative to the Sun, perhaps 50 or 60 kilometers per second, fast enough to cross the distance from Earth to Moon in a couple of hours. The trajectory tells a story written in velocity vectors and gravitational potential. 3I Atlas approached from the direction of Lyra, descending at an angle toward the ecliptic plane, its path determined by initial conditions set long ago in some other stellar system, and modified only slightly by distant encounters with stars during its interstellar journey. Upon entering the Sun's sphere of gravitational influence, a region extending perhaps a light year or two from our star, where solar gravity begins to dominate over galactic tidal forces, the object's path began to curve, slowly at first, imperceptibly, the trajectory bending by fractions of a degree per million kilometers traveled, then faster as distance closed and gravitational acceleration increased according to the inverse square law. By the time it crossed Neptune's orbit, the curvature was obvious. By Jupiter's distance, the Sun dominated its motion completely, pulling it inward at accelerating speeds, adding velocity with every moment of fall. The energy remains constant throughout. This is the iron law of celestial mechanics in the two-body problem total mechanical energy, kinetic plus potential, stays fixed in the absence of non-gravitational forces. As 3I Atlas falls inward, potential energy converts to kinetic energy. The object moves faster, but its total energy doesn't change. At perihelion, kinetic energy peaks and potential energy reaches its most negative value. But the sum remains identical to what it was at infinity, identical to what it will be after the object escapes back to interstellar space. Only took Newton and Kepler to figure this out centuries ago, working with far simpler observations than we have now, deriving universal laws from the motions of planets and moons. One mystery whispers quietly in the equations: the exact mass of 3I Atlas remains unknown, and will likely stay unknown unless the object passes very close to another body whose orbit can be perturbed measurably. Orbital mechanics depend on the ratio of masses, the reduced mass of the system, but for an object as small as a comet passing through the solar system. The Sun's mass dominates so thoroughly that the comet's own mass becomes irrelevant to its trajectory. A 1 kilogram pebble and a 1 trillion kilogram mountain follow identical paths if given identical initial positions and velocities. Mass affects gravitational force, but it also affects inertia, and the two effects cancel exactly. This is the equivalence principle that Einstein built general relativity upon, but it frustrates astronomers trying to determine physical properties of small bodies. Without mass, we cannot calculate density. Without density, composition remains ambiguous. Ice-rich objects and rock-rich objects can look identical from a distance if their sizes adjust to match their brightness. The hyperbolic excess velocity, The speed the object retains relative to the Sun, even after escaping to infinite distance, calculates to roughly 10 kilometers per second. This is the velocity 3I Atlas will carry away from the solar system, added to whatever motion the Sun itself has relative to the local standard of rest. In effect, the object will leave with nearly the same speed it arrived with, perhaps slightly faster due to the gravitational slingshot effect, depending on the geometry of its passage. The Sun will lose an infinitesimal amount of momentum in the exchange, slowed by a quantity so microscopically small that no instrument could ever detect it, while 3I Atlas gains a velocity boost of several kilometers per second. Gravity trading momentum between bodies of vastly different mass always favors the smaller object. Jupiter uses this principle to fling spacecraft toward the outer planets. The Sun uses it here, almost inadvertently, to send an interstellar visitor on a slightly faster journey back into the dark between stars. The perihelion geometry determines the outgoing trajectory, unlike a bound orbit, where the object returns to the same plane and orientation each revolution. A hyperbolic orbit passes through only once, and its exit path depends critically on the angle of approach and the perihelion distance. Small changes in initial conditions produce large differences in final outcomes. If 3I Atlas had approached from a slightly different direction, or with slightly different velocity, it might have swung past the Sun and departed toward an entirely different region of the galaxy. The specific path it follows, inbound from Lyra, outbound towards some coordinates in the southern sky, represents one possibility among infinite variations. The particular trajectory encoded in its initial state vector millions of years ago. Astronomers project the future path with the same equations that reconstructed the past. After perihelion, 3I Atlas will climb back out of the Sun's gravity well, velocity decreasing as kinetic energy converts back to potential energy, but never slowing below escape velocity. It will cross Earth's orbital distance on the outbound leg, pass Mars, reach the asteroid belt, continue through Jupiter's realm and Saturn's, coast through Uranus and Neptune's territories, each crossing taking weeks or months depending on the geometry. Eventually it will cross the heliopause, the boundary where solar wind yields to interstellar medium, roughly 100 astronomical units out, give or take, depending on direction. This crossing will take years. By then, the object will be far too faint to observe directly, its position known only through mathematical extrapolation from earlier measurements, its motion continuing whether we watch or not. Only took a few centuries of observational astronomy to develop these predictive capabilities, to look at a few points of light moving against background stars and extract complete knowledge of past and future trajectories, to compress the motion of decades or centuries into equations that fit on a single page. The mathematics cost us nothing in terms of the object's actual motion. 3I Atlas does not care that we have calculated its orbit. It does not alter its path, because we understand the curve. It simply moves, following geodesics through space-time that Newton approximated with sufficient accuracy for our purposes, continuing the journey begun long ago under some other star's light, passing through our neighborhood briefly, a visitor in the mathematical sense, bound for elsewhere. Light carries information across the void. As 3I Atlas moves closer to the Sun, growing brighter with decreasing distance, telescopes gather enough photons to spread the spectrum, to split reflected and emitted light into component wavelengths. Spectroscopy reads chemistry without touching. Atoms and molecules absorb and emit light at specific frequencies determined by quantum mechanics. Calcium absorbs at particular wavelengths, sodium at others. Water vapor shows its signature across a range of infrared lines. Carbon monoxide leaves distinct fingerprints in ultraviolet. The spectrum of a comet tells what substances surround the nucleus, what gases stream away from the warming surface, what dust particles scatter the sunlight. From this, composition emerges. The early spectra show features consistent with water vapor and carbon-bearing molecules. As sunlight heats the surface ice, sublimation begins solid, converting directly to gas without melting. The physics of vacuum and low temperature bypassing the liquid phase entirely. Water ice sublimates readily at temperatures above roughly 150 Kelvin when exposed to vacuum, releasing molecules into the coma, the diffuse cloud that surrounds every active comet. Carbon dioxide sublimates at even lower temperatures, around 70 Kelvin, which means it begins outgassing earlier in the approach, farther from the sun. Carbon monoxide is more volatile still, active at temperatures below 30 Kelvin, potentially releasing gas even in the cold outer reaches of the solar system. The relative abundances of these molecules provide clues to formation temperature, to the conditions in the protoplanetary disk, or rather, some other star's protoplanetary disk, where this ice originally condensed. Spectroscopic observations reveal hydroxyl radicals in the coma, the signature of water molecules broken apart by solar ultraviolet radiation. Parent molecules, the actual water escaping from the nucleus, survive only briefly in sunlight before photodissociation splits them into fragments. Observers see mostly the fragments, OH radicals glowing in ultraviolet, hydrogen atoms forming a vast, diffuse cloud around the comet detectable only in specific wavelengths, oxygen atoms scattered but present. The production rate of water can be inferred from the brightness of these daughter products, combined with models of how fast photodissociation occurs at different distances from the sun. Early estimates suggest modest activity, perhaps a few hundred kilograms per second of water vapor at perihelion. Maybe more, maybe less depending on how much surface area is actively sublimating. Dust appears in the spectrum as a continuum sunlight reflected from small solid particles that don't have sharp absorption features, just a smooth distribution of brightness across wavelengths with subtle slopes that hint at composition. Silicate dust, common in comets, shows a gentle rise in infrared wavelengths. Organic compounds, complex carbon-based molecules polymerized by radiation over millions of years, can darken the overall spectrum, reducing reflectivity across the board. The dust-to-gas ratio remains uncertain this early in observations, but will become clearer as more detailed spectra accumulate. Some comets are dust-rich, trailing long tails of particles that catch sunlight beautifully. Others are gas-rich, producing fainter tails dominated by ionized molecules pushed by solar wind rather than radiation pressure. Only took a few observations to realize comets come in varieties, not a single template, each nucleus carrying its own proportion of ice and rock and organic sludge. One detail emerges quietly from the spectral analysis, the presence of certain isotopic ratios, particularly deuterium to hydrogen. Deuterium, heavy hydrogen with an extra neutron, forms in trace amounts during Big Bang nucleosynthesis and gets incorporated into molecules alongside normal hydrogen. The ratio of deuterium to hydrogen in water, usually expressed as DH, varies depending on where and when the ice formed. Solar system comets show a range of DH ratios, some similar to Earth's oceans, others significantly higher, suggesting formation in colder regions of the protoplanetary disk, where deuterium enrichment occurred more readily. Measuring DH in 3I Atlas would provide direct comparison between our solar system's comets and this visitor from elsewhere, potentially revealing whether ice chemistry varies between stellar systems or remains roughly universal. But detecting deuterium requires extremely high-resolution spectroscopy. capturing subtle shifts in molecular line positions, and the object may not grow bright enough for such detailed measurements. The observation remains aspirational, a data point that would be lovely to have but may slip past uncollected. The spectrum also reveals what is not present, or at least not prominent. No strong emission from cyanogen or diatomic carbon in the early observations, though these species sometimes appear in comet spectra as the object nears perihelion. No obvious ammonia, which sublimates at temperatures similar to water but shows up less frequently in spectra, perhaps because ammonia ice is rare in comet nuclei, or perhaps because ammonia gets destroyed quickly by solar radiation once released. The absence of certain molecules tells a story as much as their presence does constraints on composition, limits on what could be abundant in the nucleus. Only so many volatiles exist that sublimate readily and survive long enough in sunlight to be detected spectroscopically. The production rates evolve as distance changes. At 6 astronomical units, when 3I Atlas was first detected, any outgassing would have been minimal, perhaps carbon monoxide if the nucleus contains significant amounts, but likely nothing else active at that temperature and solar flux. By 4 astronomical units, carbon dioxide might begin contributing measurably to the coma. By 2 astronomical units, water starts dominating the gas production. At perihelion, half an astronomical unit from the Sun, water production peaks, along with whatever other volatiles survive in the nucleus. The activity curve, a plot of gas production versus distance, traces the thermal evolution of the surface. The progressive warming as sunlight intensity increases with the inverse square of distance. The deepening penetration of heat into subsurface layers. Comets respond to sunlight on timescales of hours to days, thermal waves diffusing slowly through porous ice, driving sublimation from depths of centimeters or meters below the surface, depending on porosity and thermal conductivity. One mystery remains embedded in the spectroscopic data: the exact nature of the organic compounds present. All comets observed so far carry complex organic molecules, carbon-based compounds, ranging from simple methane and formaldehyde to elaborate macromolecules resembling biological tars and resins. These organics form through radiation chemistry in icy grains, cosmic rays and ultraviolet light, driving reactions over millions of years, building complexity molecule by molecule. The organics contribute to the dark appearance of most comet nuclei, which reflect only a few % of incident sunlight, darker than coal, despite being primarily ice. But identifying specific organic species requires detailed spectroscopy in infrared and ultraviolet, and even then, many compounds remain ambiguous, their spectral signatures overlapping, their abundances uncertain. 3I Atlas carries its own suite of organic molecules, synthesized in some other star's Oort cloud or scattered disk, but exactly which compounds and in what proportions may remain unknown unless the spectrum is analyzed with extraordinary care and sensitivity. The light continues arriving, photons that left the comet's vicinity hours ago, traveling at 300,000 kilometers per second across the inner solar system, entering telescope apertures, focusing onto spectrographs, diffracting through gratings, landing on detectors that convert photons to electrons to digital counts. Each spectrum captures a moment, the state of the coma at a specific time, the production rate of specific molecules at a specific distance from the Sun, averaged over many observations. A picture of composition emerges, incomplete but informative. A chemical census of an object from beyond the solar system. A sample of ice that condensed from a protoplanetary disk we will never see, around a star we cannot identify, carried here by chance and gravity after wandering the galaxy for longer than complex life has existed on Earth. The approach continues through planetary space. 3I Atlas crosses the orbital distance of Jupiter, though Jupiter itself lies elsewhere in its orbit during this passage, separated by hundreds of millions of kilometers, exerting negligible gravitational influence. The comet moves through regions where the king of planets normally dominates, where its massive gravity shapes the asteroid belt's inner edge, where Trojan asteroids cluster at stable Lagrange points, where captured moons orbit in retrograde testimony to ancient collisions. But space is vast even here, and orbital dynamics depend on proximity. Jupiter affects this visitor not at all, a missed encounter by astronomical accident of timing. Had 3I Atlas arrived a decade earlier or later, the geometry might have arranged a close passage, a gravitational deflection that would alter the outbound trajectory significantly. Instead, the two bodies ignore each other, following separate curves through the same general volume of space. The heliocentric velocity increases steadily. At Jupiter's distance, roughly 5 astronomical units from the Sun, 3I Atlas moves perhaps 15 kilometers per second relative to the solar system's center of mass. By the time it reaches Mars's orbital distance, velocity has increased to 30 kilometers per second. At Earth's distance, 40 kilometers per second. These speeds accumulate through gravitational acceleration, the object falling toward the Sun under an attractive force that grows stronger with decreasing distance, according to Newton's inverse square law. Every meter closer to the Sun adds a tiny increment of velocity. Integrated over astronomical unit after astronomical unit, the increments sum to significant changes in speed. The physics is simple: potential energy converts to kinetic energy in a conservative system where total mechanical energy remains constant. The experience, if the comet could experience, would be one of endless falling, accelerating perpetually toward a destination it will overshoot and then flee from. Brightness increases with decreasing distance, but not linearly. Two effects compound first. The object receives more sunlight per unit area as it approaches, following the inverse square law of illumination. Second, the object appears larger in angular size as seen from Earth, or from any vantage point in the inner solar system, also following inverse square behavior, combined. These effects mean that a comet's brightness increases as the inverse fourth power of distance, quadrupling with each halving of range. At 3 astronomical units, 3I Atlas might appear magnitude 16, requiring moderate amateur telescopes to detect. At 1.5 astronomical units, magnitude 12, visible in small instruments. At perihelion, potentially magnitude 8 or 9, naked eye visibility if the geometry places it favorably in Earth's sky, though this depends on many factors, including dust production, gas activity, and the angle of sunlight scattering off the coma. Only took a few doublings of brightness to transform the comet from a faint speck requiring professional equipment into something casual observers might glimpse on a dark night. Given patience and dark skies, the warming proceeds layer by layer. Solar radiation penetrates only millimeters into cometary ice absorbed in the uppermost surface, heating the exterior rapidly while deeper layers remain cold. Heat conducts inward slowly through porous ice, perhaps a few centimeters per day, depending on thermal diffusivity, which itself depends on porosity and composition. The nucleus likely consists of loosely aggregated material, more snowbank than solid block, filled with void spaces and structural weaknesses inherited from gentle accretion in a protoplanetary disk. Thermal waves diffuse into this material, raising subsurface temperatures gradually, triggering sublimation at depths where vapor pressure builds until gas escapes through the porous overburden. The result is sustained outgassing that can continue for hours after the surface rotates into night, driven by heat stored in subsurface layers. Comets do not turn off instantly when facing away from the sun. They exhale slowly, releasing stored thermal energy as sublimation continues beneath the surface. Rotation likely affects the activity pattern. Most comet nuclei spin with periods ranging from hours to days, presenting different faces to sunlight as they rotate, creating a day-night cycle that drives temperature variations across the surface. Some regions may be more active than others, areas rich in volatile ice, or terrain facing more directly toward the sun at perihelion, or spots where subsurface ice remains accessible despite surface desiccation elsewhere. Observers sometimes detect jets or discrete outgassing regions in detailed images of Comet Comet, localized areas where activity concentrates. Whether 3i Atlas exhibits such features remains to be seen, dependent on spatial resolution achievable with available telescopes at the distances involved. The rotation period itself remains unknown at this stage, measurable perhaps through light curve analysis if the nucleus shows enough brightness variation as it spins, but ambiguous if the nucleus is roughly spherical or if activity smears out the rotational signal. The inner solar system environment differs from interstellar space in ways beyond mere temperature. Solar wind, a continuous outflow of charged particles from the sun's corona, mostly protons and electrons streaming outward at several hundred kilometers per second, begins to interact with the comet's coma. Ultraviolet radiation ionizes some fraction of the gas molecules escaping from the nucleus, creating a population of ions that respond to magnetic fields embedded in the solar wind. These ions get swept into a tail pointing generally away from the sun, carried by the solar wind's magnetic field lines. Neutral gas and dust, by contrast, form separate tails shaped by radiation pressure and orbital mechanics. The multi-component structure of comet tails reflects this differentiation. Ion tails pointing directly away from the sun, straight and blue from carbon monoxide ions glowing in sunlight. Dust tails curving gently along the comet's orbital path, yellowish from reflected sunlight off small particles. Only took centuries of comet observations to decode this structure, to realize tails always point away from the sun, regardless of the comet's direction of motion. To understand that solar wind and radiation pressure dominate over the comet's own gravity and momentum in shaping these ephemeral features, one mystery persists quietly. The nucleus size remains poorly constrained. Brightness depends on both size and albedo. A large, dark object can appear identical to a small, bright object at the same distance, without resolving the nucleus spatially, which requires either close spacecraft passage or extraordinary angular resolution from ground-based instruments. Size estimates remain ambiguous. Typical comet albedos range from 2 to 6%, darker than charcoal, reflecting the organic-rich composition of their surfaces. Assuming an albedo in this range and using the observed brightness, astronomers estimate the nucleus diameter at perhaps several hundred meters, maybe a kilometer, possibly more. The uncertainty spans a factor of 2 or 3. A future stellar occultation, the comet passing in front of a background star and briefly blocking its light, might provide a precise size measurement if the geometry and timing work out favorably, but such occultations require luck and careful planning. More likely, the exact size of 3i Atlas will remain uncertain, a parameter constrained only loosely by indirect observations. The trajectory continues to curve. The hyperbolic path bends most sharply where gravitational force is strongest nearest the sun. At distances of several astronomical units, the curvature is gentle, barely noticeable over short time intervals. At 1 astronomical unit, the bending becomes pronounced, the path arcing visibly toward the sun over the course of days. At perihelion, The curvature peaks, the comet swinging through its closest approach in a tight arc that carries it from inbound to outbound motion over a span of hours, moving fastest, turning most sharply, experiencing maximum gravitational acceleration and maximum solar heating simultaneously. Afterward, the curve gradually straightens as distance increases and solar gravity weakens, asymptotically approaching a straight line at infinite distance, the hyperbolic trajectory blending into a constant velocity cruise through interstellar space. Only took a few months to fall from detection distance to perihelion, trading potential energy for kinetic energy under the sun's gravity well, following a path that billions of comets have followed before, though none quite like this one, none arriving from interstellar space with hyperbolic excess velocity and composition forged around another star. Perihelion arrives as a point on the calendar, a moment when distance reaches its minimum. 3i Atlas swings past the Sun at 0.47 astronomical units, roughly 70 million kilometers closer than Earth ever comes, though still well outside Mercury's orbit, which dips to 46 million kilometers at its own perihelion. The geometry places the comet slightly above the ecliptic plane during closest approach, the 60-degree inclination carrying it through inner planetary space at an angle, crossing through rather than moving along the disk where planets orbit. Solar flux at this distance reaches approximately 4.5 times Earth's baseline, intense enough to raise surface temperatures on the sunlit side to 400 or 500 Kelvin, hot enough that water ice sublimates vigorously, violently by the standards of ice in vacuum. The nucleus, perhaps a kilometer across, perhaps smaller, rotates through the intense radiation. One hemisphere faces the sun, receiving full illumination, while the opposite hemisphere experiences night, cooling slowly, releasing stored heat through thermal emission and residual sublimation from warm subsurface layers. The rotation period, unknown but likely measured in hours, determines how long each patch of surface remains in sunlight, how deeply heat can penetrate before the surface rotates away, how much thermal energy accumulates versus dissipates. A slow rotator, turning once per day or longer, would develop extreme temperature contrasts between day and night sides, driving asymmetric outgassing. A fast rotator, spinning every few hours, would distribute heat more evenly, producing more uniform activity around the nucleus. Either way, gas streams away from the warming ice at speeds of several hundred meters per second, the typical thermal velocity for water molecules at these temperatures, fast enough to escape the nucleus's negligible gravity, which amounts to perhaps a few millimeters per second squared at the surface of such a small body. Production rates peak in these hours of closest solar passage. Water vapor escapes at perhaps 1,000 kilograms per second, possibly more if the surface is particularly active, or if exposed ice covers a substantial fraction of the sunlit hemisphere. Carbon dioxide contributes additional mass, along with carbon monoxide if any remains in the nucleus, this deep into the warming process, though the most volatile ices may have been depleted during previous passages closer to some other star, or during the long approach through our outer solar system. Dust particles, silicate grains, organic particles, aggregates of minerals and frozen volatiles lift off with the gas, dragged along by sublimating ice, following ballistic trajectories away from the nucleus. The larger particles, millimeter-sized or bigger, travel slowly, barely escaping the nucleus's weak gravity, eventually falling back or settling into orbits around the comet. The smaller particles, micron-sized dust, accelerate more readily, pushed by gas drag, eventually caught by solar radiation pressure and driven into the tail. Only took a few hours at perihelion to release more mass than months of distant outgassing combined. The sublimation rate scaling exponentially with temperature. Ice evaporating thousands of times faster at 400 Kelvin than at 200 Kelvin. The coma expands to its maximum extent during this passage. Gas molecules stream outward at hundreds of meters per second, colliding with each other near the nucleus where densities remain high enough for collisions to matter, then flying ballistically once they reach altitudes where the mean free path exceeds the remaining distance to open space. Photodissociation begins immediately, solar ultraviolet radiation splitting water molecules into hydroxyl and hydrogen, hydroxyl into oxygen and hydrogen, the fragments scattering into an ever larger cloud. The coma can grow to hundreds of thousands of kilometers across, larger than Jupiter's diameter, though its density remains so low that the total mass of gas amounts to perhaps a few 100,000 kilograms, less than a loaded freight train, spread across a volume large enough to swallow multiple Earths. Cometary atmospheres exist only in the technical sense. They are mostly vacuum, just slightly less vacant than the surrounding interplanetary medium. Solar wind compresses the coma on the sunward side, the supersonic flow of charged particles from the sun creating a bow shock where the plasma impacts the comet's ionized gas. Magnetic fields embedded in the solar wind drape around the coma, creating a magnetosphere in miniature, a region where the comet's own plasma dominates over the interplanetary background. The ion tail forms here. Molecules ionized by solar ultraviolet, then swept away by the solar wind's magnetic field, carried anti-sunward at hundreds of kilometers per second, forming a tail that can extend tens of millions of kilometers, thin and straight, glowing faintly blue from ionized carbon monoxide. The dust tail develops separately, particles pushed by radiation pressure, sunlight imparting momentum to dust grains, a pressure amounting to only a few micropascals, but sufficient to accelerate tiny particles over days and weeks. Dust tails curve gently, following the comet's orbital path, yellowish from reflected sunlight, broader and more diffuse than ion tails. Only took a few perihelion passages to erode a comet significantly, each orbit stripping away surface layers, exposing deeper ice, gradually consuming the nucleus until only inert rock remains, or until the nucleus fragments from thermal stress and tidal forces, scattering into a meteoroid stream. One detail emerges from perihelion observations: the non-gravitational effects become measurable. Outgassing exerts forces on the nucleus rocket thrust from jets of vapor escaping the surface. These jets are not uniformly distributed and not symmetrically oriented, so they create net forces that alter the trajectory slightly. A comet with most of its activity on the sunward hemisphere experiences a force pushing it away from the sun. A comet with activity concentrated on one side due to rotation and surface heterogeneity experiences transverse forces that change the orbital elements. The effects are tiny accelerations of micrometers per second squared, barely detectable even with precise astrometry, but they accumulate over time, altering the trajectory by kilometers or tens of kilometers relative to a purely gravitational path. For 3I Atlas, these non-gravitational accelerations introduce uncertainty into predictions of the outbound trajectory, small deviations that compound over the months and years following perihelion. Only so much precision is possible when the object itself is pushing back against the forces trying to define its path. The velocity at perihelion reaches approximately 55 kilometers per second relative to the Sun. This is the maximum speed along the entire trajectory, the point where kinetic energy peaks and potential energy bottoms out. At this velocity, the comet crosses its own diameter in 10 or 20 seconds. It traverses the distance from Sun to Earth, 1 astronomical unit, in about 30 hours. The speed feels absurd by terrestrial standards, though it pales compared to particles in the solar wind, which stream past at several times this velocity, or compared to light itself, which makes the same journey in 8 minutes. Still, for a mountain of ice and rock moving through space under nothing but gravity and momentum, 55 kilometers per second represents profound speed, energy accumulated through a long gravitational fall, potential converted to kinetic in perfect accordance with conservation laws written into the structure of space-time. The moment of closest approach passes without ceremony. There is no discontinuity, no sudden change. The comet simply reaches the point on its trajectory where distance to the Sun stops decreasing and begins increasing. The perihelion point, defined mathematically more than physically, a coordinate where the radial component of velocity equals 0, while the tangential component reaches maximum. From the nucleus's perspective, if ice could perceive, there would be only continuous motion, continuous acceleration, a smooth arc through gravitational field lines. The Sun growing larger in angular size, then shrinking again. The flux of radiation increasing, then decreasing. But all of it gradual, all of it predictable from the equations governing two-body dynamics. Only took a few hours to pass through perihelion, the closest point, the hottest moment, the peak of activity, and then the long climb back out begins. Velocity still high, but decreasing now. Distance increasing. The comet beginning its journey back toward the cold outer system and eventually beyond. The outgassing does not push uniformly. Jets emerge from discrete regions on the nucleus, concentrated areas where subsurface ice remains accessible or where surface morphology channels vapor into preferred directions. These jets act as tiny rocket engines, each one exerting force in the direction opposite to the gas flow. A jet pointing sunward pushes the nucleus away from the Sun. A jet oriented tangentially to the orbit imparts velocity perpendicular to the radial direction. The total force depends on the mass flow rate and the velocity of the escaping gas momentum carried away by molecules, transferred as equal and opposite momentum to the nucleus itself, for a production rate of 1,000 kilograms per second and escape velocities around 500 meters per second. The net force might amount to several hundred newtons, perhaps 1,000 at peak activity, applied to a nucleus with mass of perhaps 1 billion kilograms, assuming a kilometer-sized body with density around 500 kilograms per cubic meter, typical for porous cometary material. This yields an acceleration of about 1 micrometer per second squared, give or take an order of magnitude depending on exact parameters. The acceleration seems negligible, and by everyday standards it is. 1 micrometer per second squared accumulates to about 1 centimeter per second of velocity change over 3 hours, or about 30 centimeters per second over a day. But integrated over weeks and months as the comet remains active, these small changes compound. A velocity change of 1 meter per second, accumulated over a month of continuous outgassing, translates to position changes of thousands of kilometers by the time the comet crosses Jupiter's orbit on the outbound leg. The trajectory diverges from the pure Keplerian prediction, the path calculated assuming only gravitational forces by measurable amounts. Astrometric observations reveal the discrepancy. The comet appears slightly ahead of or behind its predicted position, or displaced perpendicular to the orbital plane, depending on the orientation and timing of the outgassing. Only took a few decades of careful comet observations in the 20th century to realize that trajectories deviate from gravitational expectations, that some additional force acts on these bodies, and only a few more years to identify sublimation-driven jets as the culprit. The direction of the non-gravitational force depends on the rotation state and the distribution of active regions. If the nucleus rotates with its spin axis perpendicular to the orbital plane, and if most activity concentrates on the sunward hemisphere, the force points roughly radially away from the Sun, producing what astronomers call a radial, non-gravitational acceleration. This primarily affects the semi-major axis and period of bound orbits, though for hyperbolic trajectories like 3I Atlas, it alters the hyperbolic excess velocity and the perihelion distance of the outbound path relative to the inbound path. If the nucleus rotates with a different orientation, or if active regions are distributed asymmetrically around the rotation axis, transverse forces develop components perpendicular to the Sun-Comet line. These transverse forces can change the inclination, or shift the orbital plane, or alter the timing of when the comet crosses certain distances. The effect is a subtle rewriting of the trajectory through forces measured in micronewtons but integrated over months. Modeling the non-gravitational accelerations requires assumptions about the nucleus that remain largely unknown. The rotation period, the orientation of the spin axis, the location and strength of active regions, the albedo and thermal properties of the surface, all of these affect how much force develops and in which direction. Astronomers typically parameterize non-gravitational effects using empirical terms in the equations of motion. Coefficients labeled A1, A2, A3 that represent radial, transverse, and out-of-plane accelerations, scaled by some function of distance from the Sun to account for the temperature dependence of sublimation rates. These parameters are fit to astrometric observations, adjusting their values to minimize the discrepancy between observed and predicted positions. The approach works pragmatically, allowing accurate orbit determination despite incomplete physical understanding. But the fitted parameters do not necessarily correspond to any specific physical configuration of the nucleus. Many different combinations of rotation state and active region distribution could produce the same overall acceleration. Only so much can be inferred from distant observations of position versus time. One mystery embedded in the outgassing behavior, the so-called rocket effect, varies with distance in ways that sometimes deviate from simple models. Standard sublimation theory predicts that gas production rate should scale as a power law with solar flux, which itself scales as inverse distance squared. This implies non-gravitational acceleration should follow a similar power law, strongest at perihelion and weakening rapidly with increasing distance. Observations generally confirm this pattern, but with deviations. Some comets show activity that persists longer than expected as they recede from the Sun, suggesting subsurface ice continues sublimating from stored heat. Other comets exhibit asymmetries between inbound and outbound legs, producing more gas before perihelion than after, or vice versa, possibly due to surface evolution or mantling by dust that reduces sublimation efficiency. 3I Atlas may or may not follow the standard pattern, its behavior determined by thermal properties and surface composition that evolved in some other stellar system under conditions that may differ from our own solar nebula. The jets themselves remain largely invisible in most observations. What telescopes see is the coma, the diffuse cloud of gas and dust surrounding the nucleus, which appears roughly symmetrical unless imaged with high spatial resolution. Discrete jets show up as small-scale enhancements in brightness, streamers or fans extending from the nucleus region, visible only when the seeing conditions are excellent and the angular resolution sufficient to resolve structure on scales of a few hundred kilometers at the comet's distance. Most observations lack this resolution, seeing instead the integrated glow of the entire coma, a smoothed-out average of all the activity happening on the nucleus. The non-gravitational accelerations provide indirect evidence that jets exist and that they break the spherical symmetry of outgassing, even when the jets themselves cannot be photographed directly. Only by tracking position over weeks and months, comparing to gravitational predictions, Measuring the systematic offset that accumulates, can the presence and orientation of net thrust be inferred? The magnitude of the force depends on the sublimating species. Water dominates for most comets at distances less than about 3 astronomical units from the Sun. But carbon dioxide can be significant if present in high abundance, and carbon monoxide contributes at larger distances where water ice remains frozen. Each volatile carries different momentum per molecule. Lighter molecules move faster at a given temperature, and thus carry more momentum for the same mass loss rate. Carbon monoxide. With molecular weight, 28 escapes faster than water vapor, with molecular weight 18, and both escape faster than carbon dioxide, molecular weight 44. The composition of the escaping gas therefore affects the rocket efficiency. A comet venting pure carbon monoxide generates more thrust per kilogram of mass loss than one venting pure water, but water is far more abundant in most comet nuclei, so despite its lower efficiency per molecule, it dominates the net force simply through greater production rate. Only took careful spectroscopy and gas production measurements to map out which volatiles contribute most to activity at different distances, building a census of comet composition that continues to refine with each new object observed. The effect diminishes as the comet recedes from perihelion. Solar flux decreases with the square of distance. Surface temperatures drop. Sublimation rates decline exponentially with cooling, and the non-gravitational acceleration fades. By the time 3I Atlas crosses Earth's orbital distance on the outbound leg, several weeks after perihelion, the acceleration has likely fallen to a fraction of its peak value. By 2 astronomical units, several months out, it may be negligible. By Jupiter's distance, nearly a year after perihelion, outgassing has probably ceased entirely, except for the most volatile ices. If any remain, the trajectory by then is essentially Keplerian again, determined purely by gravity and the velocity vector accumulated during the active phase. The non-gravitational forces leave their mark as a permanent change in the trajectory, a slight shift in the hyperbolic excess velocity, a small alteration in the direction of departure, but they no longer actively push once the surface cools below sublimation temperatures. Only took a few months of activity to write the final trajectory, to add the subtle deviations that distinguish the actual path from the idealized gravitational curve, and then silence returns, the nucleus dormant, coasting on momentum and gravity alone toward the interstellar medium. The tail develops as a consequence of mass loss, material streaming away from the nucleus faster than it can fall back. Gas molecules, once liberated from surface ice, travel outward at thermal velocities hundreds of meters per second, far exceeding the escape velocity from the nucleus, which amounts to less than 1 meter per second for a kilometer-sized body. The gas expands freely into vacuum, colliding with other molecules near the nucleus where densities remain high, then flying ballistically once the mean free path grows longer than the distance to empty space. Some molecules survive for hours in sunlight before photodissociation breaks them apart. Others ionize within minutes, ultraviolet photons stripping electrons and converting neutral gas into plasma. The ions respond to magnetic fields embedded in the solar wind, accelerated anti-sunward along field lines, forming the ion tail a narrow, straight feature pointing directly away from the sun, regardless of the comet's direction of motion. Dust follows a different trajectory. Solid particles, ranging from nanometer-sized grains to centimeter-sized pebbles, lift off with the sublimating gas, dragged along by collisions with outflowing molecules. Near the nucleus, gas drag dominates, accelerating dust to velocities approaching the gas velocity, perhaps a few hundred meters per second for the smallest grains. But as the gas density drops with distance, Radiation pressure takes over sunlight, imparting momentum to particles through absorption and scattering, a force that scales with particle cross-section but not with mass, favoring smaller grains over larger ones. Micron-sized dust experiences radiation pressure comparable to solar gravity, sometimes exceeding it, resulting in net acceleration away from the sun. Larger particles feel weaker radiation pressure relative to their inertia and fall into trajectories that curve only gently away from the comet's orbital path. The result is a dust tail, a broad, curved structure tracing the comet's motion through space, composed of particles sorted by size and departure time, the smallest and most recent grains farthest from the nucleus, the larger and older particles lagging behind in the comet's wake. The tails can extend millions of kilometers, sometimes tens of millions, vast structures that dwarf the nucleus itself by factors of 10,000 or more, yet they contain remarkably little mass. An ion tail might hold a few hundred kilograms of plasma spread across 10 million kilometers, an average density far lower than the best laboratory vacuum. A dust tail might contain a few thousand kilograms of solid particles distributed along a similar length, concentrations so tenuous that spacecraft could fly through without significant collision risk, though the occasional dust impact at tens of kilometers per second would deliver substantial energy to any surface it struck. The tails exist as visible phenomena primarily because they scatter or emit light, efficiently dust reflecting sunlight, ions fluorescing in ultraviolet, not because they constitute significant mass. Only took a few bright comets visible to naked eye observers to establish that tails always point away from the sun, a fact noted centuries before anyone understood the mechanism, before solar wind and radiation pressure were discovered and quantified. The ion tail shows structure when observed with sufficient resolution. Streamers and rays appear, features aligned with magnetic field lines, tracing the topology of the solar wind's field as it drapes around the coma. Sometimes the tail disconnects entirely, a disconnection event where a segment of the tail breaks free and drifts away, while a new tail forms closer to the nucleus. These events occur when the comet crosses a boundary in the interplanetary magnetic field, a region where field lines change orientation, causing the magnetic connection between the coma and the solar wind to reconfigure suddenly. The disconnected tail continues moving anti-sunward, fading over hours or days as the ions recombine with electrons and the plasma cools, while the new tail grows to replace it. The phenomenon demonstrates the dynamic nature of comet-solar wind interaction, the way these tenuous structures respond in real time to changes in the space environment. Dust particles follow ballistic trajectories after leaving the coma's immediate vicinity, each grain tracing its own orbit around the sun, perturbed slightly by radiation pressure and the Poynting-Robertson effect, a subtle drag force that causes orbiting dust to spiral slowly sunward over thousands or millions of years. The largest particles, millimeter-sized or bigger, barely feel radiation pressure and follow orbits nearly identical to the comet's path, spreading along the orbital arc, forming a meteoroid stream that persists long after the comet has moved on. If Earth's orbit intersects this stream, the particles enter the atmosphere as meteors, visible as streaks of light from atmospheric friction, sometimes occurring in annual showers associated with specific comets. The Perseids trace back to Comet Swift-Tuttle. The Leonids originate from Comet Tempel-Tuttle. Each meteoroid stream maps the historical orbit of its parent comet. Dust laid down over multiple returns, spread along the trajectory by planetary perturbations and radiation forces. 3I Atlas will not produce a meteoroid stream that Earth encounters. The hyperbolic trajectory ensures its dust remains far from our planet's path, but the particles it sheds will continue orbiting the Sun for millennia. gradually spiraling inward, eventually falling into the sun or colliding with a planet. Individual grains carrying trace memories of an interstellar origin. One detail appears in high-resolution images when conditions allow multiple dust tails, or rather a single dust tail showing gradients in curvature corresponding to different particle sizes. The smallest grains, pushed strongly by radiation pressure, form a narrow, nearly straight tail extending anti-sunward. Intermediate-sized particles curve more gently, creating a broader fan of material. The largest particles, barely accelerated by radiation, lag close to the orbital path, forming a short, stubby tail that points almost backward along the direction of motion. Viewed together, these size-sorted populations create the appearance of multiple tails, or a tail with complex structure. A synchrone pattern where each curve traces the trajectory of particles released at the same time, but with different sizes, only took careful photographic analysis in the 20th century to decode this structure, to realize that what appears as tail multiplicity actually reflects the continuum of particle sizes and radiation pressure responses. Each grain following physics that depends on its surface, area to mass ratio. The tail material disperses into interplanetary space, atoms and molecules and dust grains joining the diffuse background of material that fills the solar system. The hydrogen atoms released by photodissociation of water molecules eventually reach distances of tens of millions of kilometers from the comet, forming a vast, tenuous cloud detectable only in specific ultraviolet wavelengths. Oxygen atoms, also produced by water dissociation, scatter more slowly but contribute to the faint glow observable in certain emission lines. Carbon, nitrogen, sulfur, all the elements incorporated into cometary ice disperse into the inner solar system, contributing minutely to the interplanetary medium's composition, adding to the slow accumulation of dust and gas that cycles through the sun's domain over millions of years. Comets have been doing this since the solar system formed, injecting material into interplanetary space with every perihelion passage, slowly eroding away their initial mass, distributing volatiles and refractories throughout the planetary region. Only so many orbits can occur before a comet exhausts its ice, becoming a dormant nucleus, indistinguishable from an asteroid except for its orbit and perhaps traces of organic material on its surface. The activity peaks, sustains briefly, then begins to decline as 3I Atlas recedes from perihelion. The tails remain visible for weeks, even months, slowly fading as production rates decrease with cooling and increasing distance. The ion tail shortens first, its plasma requiring continuous replenishment to remain visible, disappearing within days once gas production drops below a threshold. The dust tail persists longer, particles already launched continuing to scatter sunlight even after new dust stops lifting off the nucleus. Eventually, perhaps a few months past perihelion, the comet appears tailless again, or nearly so, a condensed coma without obvious extension, reverting to the appearance it had during approach, before perihelion activity began in earnest. The tail material spreads throughout the inner solar system, a cloud of atoms and grains that will never reassemble, dispersed permanently by radiation, solar wind, and orbital dynamics. The comet's temporary exhalation mixing into the vast volume of interplanetary space, imperceptible against the background, unless measured with sensitive instruments tuned to specific wavelengths or particle types. The nucleus itself remains hidden beneath the coma, a small solid body obscured by the cloud of gas and dust surrounding it. Direct observation of the nucleus requires spatial resolution, far exceeding what most telescopes can achieve at distances of several astronomical units. The angular size of a kilometre-wide object at one astronomical unit, roughly 150 million kilometres, amounts to about 0.001 arcseconds, far smaller than the seeing disk produced by Earth's atmospheric turbulence, which rarely dips below half an arcsecond even at excellent observing sites. Space-based telescopes avoid atmospheric blurring, but still face diffraction limits determined by aperture size. The Hubble Space Telescope, with its 2.4-meter mirror, achieves diffraction-limited resolution of roughly 0.05 arcseconds in visible light, still 50 times too coarse to resolve a kilometre-sized nucleus at one astronomical unit. Only spacecraft approaching to within a few thousand kilometres can image comet nuclei with sufficient detail to discern shape and surface features. 3I Atlas will receive no such visit. It passes through the inner solar system without dedicated mission, without close flyby, its nucleus remaining a point source obscured by its own atmosphere. What can be inferred comes from indirect measurements. The total brightness, combined with assumptions about albedo, constrains the size probably somewhere between a few hundred meters and a couple of kilometers in diameter. The uncertainty reflecting the unknown reflectivity. The color of the dust, measured through multi-wavelength photometry, suggests composition typical of solar system comets, silicate minerals mixed with dark organic compounds. Perhaps some metallic inclusions, the exact proportions ambiguous. The production rates of gas and dust, estimated from spectroscopy and photometry, imply surface activity consistent with a moderately active comet, not as vigorous as some sun-grazing comets that pass within solar radii of the photosphere, not as dormant as extinct comet candidates that show no detectable outgassing. Only so much can be determined from light alone. Photons carrying information about brightness and wavelength, but not about three-dimensional structure or surface texture. The shape remains entirely unknown. Comet nuclei observed by spacecraft show remarkable diversity, some nearly spherical, others highly elongated, some bilobed with distinct regions connected by narrow necks, others irregular with prominent pits and scarps and flat regions. The shapes reflect formation processes and collisional history, gentle accretion in protoplanetary disks producing loosely bound rubble piles, subsequent impacts and tidal encounters reshaping the bodies over billions of years. Some nuclei may be contact binaries, two separate objects that collided at low velocity and stuck together, their shared gravity barely sufficient to resist tidal forces during close solar passages. Others may be monolithic, single coherent bodies that fractured over time from thermal stress or outgassing forces, but retained overall structural integrity. Without resolved images, the shape of 3I Atlas remains a mystery, describable only statistically, probably irregular, possibly elongated, perhaps composed of multiple lobes, but these are expectations based on samples from solar system comets, not direct measurements of this particular object. Rotation introduces variability in brightness, the nucleus presenting different cross-sections to observers as it spins. A spherical nucleus shows minimal brightness variation with rotation. An elongated or irregular nucleus displays significant changes. The brightness curve rising and falling with a period equal to the rotation period, or half the rotation period if the body is roughly symmetric. Light curve analysis can reveal the rotation period and provide crude constraints on shape, how elongated, how irregular, but requires sustained photometric monitoring over many rotation cycles. Observations often difficult to obtain for faint comets obscured by coma activity. Early attempts to measure 3I Atlas's rotation may yield ambiguous results, the signals smeared by variable outgassing or lost in the noise of coma brightness variations. The rotation period might be hours or days, The spin axis oriented arbitrarily relative to the orbit, the shape anything from nearly round to highly elongated. Only took spacecraft observations of a few dozen comet nuclei to establish that no two are exactly alike. Each nucleus presenting its own combination of size, shape, rotation, and surface properties. Internal structure remains purely speculative. Models suggest comet nuclei are porous, more void space than solid material. Densities ranging from 300 to 600 kilograms per cubic meter, less dense than water ice, despite being composed primarily of ice and rock. The porosity allows thermal waves to penetrate more deeply, permits sublimating gas to percolate through the interior, and reduces structural strength, making nuclei fragile and prone to fragmentation under stress. Some comets split spontaneously during perihelion passage, thermal gradients and outgassing forces overwhelming tensile strength, the nucleus breaking into two or more pieces that follow slightly different trajectories. Other comets survive multiple perihelion passages intact, their structure sufficient to withstand heating and rotational stress cycle after cycle. Whether 3I Atlas is fragile or robust cannot be determined without close observation, without monitoring for brightness, changes that might indicate fragmentation, without spectroscopic signatures of fresh ice exposed by surface breakup. The nucleus could be a loosely aggregated rubble pile, held together mainly by self-gravity and ice sintering, or it could be a more cohesive body, ice and rock bonded into a relatively strong matrix. Both scenarios are consistent with available observations. One mystery persists throughout the apparition: the albedo, the fraction of incident sunlight reflected from the surface. Most comet nuclei observed by spacecraft show albedos between 0.02 and 0.06, 2 to 6% reflectivity, making them among the darkest objects in the solar system, blacker than charcoal, absorbing more than 90% of incident light. The darkness arises from organic compounds coating the surface, complex carbon-based polymers produced by radiation processing of ices over millions of years, creating a lag deposit, a layer of non-volatile residue left behind as ice sublimates away, gradually mantling the surface in dark material. This mantle insulates deeper ice, reducing sublimation rates, but cannot completely suppress outgassing. Eventually the mantle fractures from thermal stress or differential sublimation, exposing fresh ice in localized regions that become active jets. The albedo of 3I Atlas cannot be measured directly without resolving the nucleus spatially, so it remains assumed based on comparison with other comets, an assumption that propagates uncertainty into all size estimates derived from brightness measurements. Surface features craters, boulders, layers, fractures, smooth plains. Rough terrain have been catalogued on every comet nucleus imaged up close, each surface telling a story of bombardment and outgassing and thermal cycling over billions of years. Some regions appear ancient, heavily cratered, suggesting surfaces that have remained stable for long periods. Other regions appear young, smooth or freshly exposed, indicating recent activity that has resurfaced the area. Layering visible in cliffs and scarps suggests that nuclei formed through accretion of smaller particles, each layer representing a different stage of growth in the protoplanetary disk, or perhaps seasonal deposits of ice during previous perihelion passages in some long-lost orbit. Without close-up images, the surface of 3I Atlas remains imagined rather than observed, a landscape that could resemble other comet nuclei or could surprise with features unique to its interstellar origin, chemistry determined by different stellar nebula conditions, surface modified by different radiation environment during its journey through the galaxy. The nucleus continues its trajectory, hidden beneath the coma, its true nature obscured by its own activity, a solid body perhaps 1,000 meters across, carrying the only direct samples of another stellar system's planetary formation environment that we will encounter in this apparition, untouchable, unreachable, destined to recede beyond observation while its physical properties remain largely unknown, inferred rather than measured, guessed rather than documented. Only took a few million years of interstellar travel to bring this object within detection range, and only a few months of visibility before it fades again. A transient opportunity to study something from elsewhere, constrained by distances too vast for spacecraft to cross in the available time, by brightnesses too faint for detailed spectroscopy, by angular sizes too small for direct imaging. The nucleus keeps its secrets, revealing only what can be extracted from integrated light and distant observation, a frustrating limitation inherent in astronomy, seeing without touching, measuring without sampling, inferring structure from shadows and spectra while the object itself remains forever out of reach. 3 interstellar visitors now populate the catalogue, each discovered within a span of less than a decade, each teaching different lessons about what drifts through the galaxy. The first, 1I Oumuamua, arrived in October 2017, detected by the Pan-STARRS telescope in Hawaii as it was already receding from the Sun, its perihelion passage having occurred weeks earlier, unnoticed. The name means scout or messenger in Hawaiian, chosen to reflect its role as first confirmed interstellar object, first proof that such wanderers exist and occasionally pass through our neighborhood. Oumuamua moved on a hyperbolic trajectory with eccentricity around 1, 2 higher than 3I Atlas, indicating greater velocity relative to the local standard of rest. Its shape appeared highly elongated based on dramatic brightness variations rotating every 7.3 hours, with amplitude suggesting an axis ratio of perhaps 10:1, cigar-shaped or possibly disc-like, though the geometry remained ambiguous without resolved imaging. The object showed no detectable coma, no cometary activity, appearing asteroidal despite its interstellar origin, though subtle non-gravitational acceleration was detected, suggesting some level of outgassing too faint to observe directly. The lack of obvious activity sparked debates about composition. Was it rocky like an asteroid, or icy like a comet with activity suppressed by a thick insulating mantle, or something else entirely? Perhaps a nitrogen iceberg from a Pluto-like world, as one model proposed. The second visitor, 2I Borisov, appeared in August 2019, discovered by amateur astronomer Gennady Borisov, using a telescope he built himself. A reminder that important discoveries sometimes come from dedicated individuals rather than large survey programs. Borisov contrasted sharply with Oumuamua, clearly cometary, showing strong activity throughout its apparition, developing a well-defined coma and tail visible in modest telescopes. Its composition appeared remarkably similar to solar system comets based on spectroscopy water vapor, carbon monoxide, dust properties consistent with long-period comets from our own Oort cloud. The similarity suggested that comet formation processes might be universal, that ices condensing in protoplanetary disks produce similar chemistry regardless of which star provides the heat and light. Borisov's eccentricity measured around 3, 4 significantly higher than either Oumuamua or 3I Atlas, indicating it originated from a stellar encounter that imparted substantial velocity, or perhaps formed in a system with different dynamical history. The nucleus appeared relatively small, perhaps half a kilometer across, fragmenting partially during its approach to perihelion, shedding pieces that drifted along similar trajectories, demonstrating the fragility of cometary nuclei subjected to thermal stress and possibly tidal forces from the Sun's gravity. Now 3I Atlas joins this sparse sample, the third confirmed interstellar object. expanding the census but hardly approaching statistical significance. 3 objects from 3 different arrival directions, 3 different eccentricities, 3 different activity levels, too few to establish patterns, too diverse to draw firm conclusions, but suggestive nonetheless. The detection rate implies that interstellar objects pass through the inner solar system regularly, perhaps several per year within Jupiter's orbit, most too small or too faint to detect with current surveys, observable only when geometry and size conspire to bring them within range of automated telescopes scanning for anything unusual. Models of planetary formation predict vast numbers of such objects ejected during the chaotic early phases of planetary system development. Jupiter-mass planets especially efficient at flinging icy bodies into interstellar space through gravitational slingshots. Each stellar system with giant planets likely produces millions or billions of exiles over its history. Comets and planetesimals, accelerated past escape velocity, sent wandering through the galaxy, multiply by hundreds of billions of stars in the Milky Way, and the galactic population of free-floating objects becomes enormous, a diffuse sea of ice and rock moving through interstellar space at typical velocities of tens of kilometers per second relative to nearby stars. The comparison between these 3 objects reveals more questions than answers. Why did Oumuamua show no obvious cometary activity, while Borisov and 3I Atlas do? Possible explanations include differences in composition, Oumuamua perhaps rocky, or mantled in inert material, or differences in thermal history. With Oumuamua having lost its volatiles during previous close passages to other stars over its lifetime, why such variation in eccentricity? And does this reflect different ejection mechanisms or different galactic encounters during transit? Borisov's high eccentricity might indicate ejection by a massive planet at high speed, or acceleration from a stellar flyby, while Oumuamua's lower eccentricity suggests gentler ejection or longer time since the last significant gravitational perturbation. 3I Atlas falls between its moderate eccentricity implying intermediate origins or histories. Only took 3 examples to demonstrate that interstellar objects are not a uniform population, but a diverse collection of bodies with different formation environments, different dynamical histories, different compositions and structures. One detail emerges from compositional comparisons. Borisov's carbon monoxide abundance appeared unusually high compared to typical solar system comets. The CO-H2O ratio exceeding what is commonly observed in Oort cloud objects. This might indicate formation in a colder region of its home protoplanetary disk, where carbon monoxide ice remained stable, or it might reflect different chemical processes in that system's nebula, a variation in the carbon-to-oxygen ratio, or in the temperature-pressure history during ice condensation. 3I Atlas's carbon monoxide abundance remains uncertain. Spectroscopic detections of CO requiring specific infrared or ultraviolet observations that may or may not be attempted with sufficient sensitivity. If 3I Atlas shows different CO-H2O ratios than Borisov, or different from solar system comets, it would strengthen the case that planetary systems produce comets with varying chemistry depending on local conditions. If all interstellar comets show similar compositions, it would suggest surprising uniformity in protoplanetary disk chemistry across the galaxy. Only so many measurements can be made before these visitors fade beyond observation, each observation potentially revealing new information or deepening existing mysteries. The orbital dynamics vary as well. Oumuamua entered from the direction of Vega, or more precisely from the solar apex, the direction the Sun is moving relative to the local standard of rest, suggesting its trajectory was nearly head-on relative to the Sun's galactic motion. Borisov entered from a different angle. Its approach direction corresponding to no particular nearby star, indicating an origin elsewhere, and a trajectory shaped by galactic dynamics rather than recent stellar encounters. 3i Atlas arrives from yet another direction. Lyra, inclined steeply to the ecliptic, its velocity vector reflecting whatever combination of ejection velocity and galactic motion carried it to this intersection with our solar system. The arrival directions appear random, as expected if these objects fill the galaxy uniformly, moving in all directions with a distribution shaped by galactic rotation and stellar velocities. Only took decades of theoretical work before these first detections to predict that interstellar objects would arrive from random directions at rates dependent on the unknown population density in local interstellar space, and only a few years of actual observations to begin testing those predictions, though the sample remains too small for robust statistical analysis. The future promises more detections as survey capabilities improve. The Vera Rubin Observatory, scheduled to begin operations soon, will scan the sky repeatedly with a large mirror and sensitive cameras, detecting faint moving objects more efficiently than current surveys. Models predict Rubin could find several interstellar objects per year, possibly dozens depending on the actual population density. Building a sample large enough to characterize properties statistically size distribution, composition frequency, eccentricity distribution, arrival rate as a function of direction. Other surveys, space-based and ground-based, will contribute additional detections. Within a decade or two, interstellar objects may transition from curiosities to a well-characterized population, their properties catalogued, their origins constrained by observations of hundreds of examples rather than 3. But for now, 3i Atlas remains one of only 3, a significant fraction of the known sample, each object precious for the information it carries about planetary formation in other systems and the dynamics of matter ejection and transport through the galaxy. The 3 visitors continue their journeys, each on its own hyperbolic trajectory, receding from the Sun along different paths toward different regions of the galaxy. Oumuamua, now beyond Neptune's orbit and fading, heads generally toward the constellation Pegasus, its velocity relative to nearby stars about 26 kilometers per second. Borisov, also beyond Neptune, moves toward different coordinates, its higher velocity carrying it away faster, covering more distance per year. 3i Atlas will join them eventually, months or years from now, crossing Neptune's distance on its outbound arc, continuing into the Kuiper Belt region and beyond. Velocity gradually decreasing as the Sun's gravity continues to pull backward, asymptotically approaching the hyperbolic excess velocity, never quite reaching it but getting arbitrarily close as distance increases. Only took a few months of observation to characterize each object well enough to predict its trajectory millennia into the future, even as the objects themselves fade beyond detection within a year or 2 of discovery. Their paths calculated, their destinies known, but their surfaces and interiors and detailed properties remaining mysteries, puzzles glimpsed briefly, then lost again to distance and darkness. The departure begins as the comet climbs away from Perihelion, velocity still high but diminishing now, kinetic energy converting back to potential energy as distance increases. The gravitational exchange follows principles worked out centuries ago: momentum conservation, energy conservation. The mathematics of two-body interactions that govern everything from planetary orbits to spacecraft trajectories to interstellar visitors passing through. The Sun loses momentum in this encounter, slowed infinitesimally by its gravitational interaction with the comet, while 3i Atlas gains momentum, accelerated by the same interaction. The momentum transfer is exactly equal and opposite. as Newton's third law requires. But because the Sun's mass exceeds the comet's by a factor of perhaps 1030, the velocity change experienced by the Sun is undetectably small, perhaps 10 to 20 meters per second, a change so minute that it would take trillions of similar encounters to alter the Sun's velocity by even a millimeter per second. The comet, by contrast, gains several kilometers per second of velocity during its perihelion passage. The gravitational assist bending its trajectory and boosting its speed relative to the Sun. This asymmetry defines gravitational slingshots. Small bodies gain substantial velocity changes when passing massive bodies, while the massive bodies experience negligible recoil. The effect scales with mass ratio and geometry. A spacecraft passing Jupiter can gain or lose kilometers per second of velocity depending on the approach angle, while Jupiter's velocity changes by an amount smaller than atomic scale measurements could detect. Planetary missions exploit this ruthlessly. Voyager spacecraft gaining speed at each giant planet encounter, accumulating enough velocity to escape the solar system entirely. Their trajectories designed decades in advance to take advantage of favorable planetary alignments. 3i Atlas requires no careful planning. It simply follows the hyperbolic path determined by its initial velocity and perihelion distance. The gravitational assist happening automatically as a consequence of orbital geometry. The Sun's gravity simultaneously bending the trajectory and increasing the comet's speed. The velocity boost comes from falling into and then climbing back out of the Sun's gravity well, but asymmetrically. The comet approaches from one direction and departs in another. The trajectory bent by roughly 180 degrees minus twice the angle the hyperbola makes with the radial direction at perihelion. This bending means the velocity vector at infinite distance differs from the approach velocity vector, rotated into a new direction. In the Sun's reference frame, the comet's speed at infinite distance equals the hyperbolic excess velocity, roughly 10 kilometers per second for 3i Atlas, but the direction has changed, pointed towards some new region of the galaxy rather than back along the approach path. In a reference frame where the Sun moves, say, the local standard of rest, or the galactic frame, this rotation of the velocity vector, combined with the velocity the Sun carries, results in the comet departing with different speed and direction than it arrived with. The effect is a genuine acceleration from the Sun's perspective. Momentum transferred gravitationally. No fuel expended. Pure orbital mechanics converting gravitational potential into kinetic energy and back again, with net changes that depend on geometry. The outbound trajectory points generally southward in ecliptic coordinates, though the exact direction depends on details of the perihelion passage, precisely where perihelion occurred, exactly what velocity perturbations accumulated from non-gravitational forces, how the orbit evolved under observational constraints. Preliminary calculations suggest departure toward coordinates in the southern sky, perhaps vaguely in the direction of Centaurus or Vela, though these are large constellations and the trajectory does not aim toward any particular star. The path will carry 3i Atlas through the southern celestial hemisphere as seen from Earth, limiting observations from northern hemisphere observatories as the comet fades, favouring southern telescopes during the months after perihelion. The inclination 60 degrees or so means the trajectory cuts across the ecliptic plane rather than staying in it. The outbound path taking the comet high above or below the planetary orbits, depending on phase, geometry carrying it through three-dimensional space rather than the flattened disk where planets reside. Distance increases steadily. A week after perihelion, the comet has receded to perhaps 0.6 astronomical units from the Sun, velocity dropping to maybe 50 kilometers per second, still moving faster than anything natural in the inner solar system except for sun-grazing comets at their closest approaches. 2 weeks out, nearly 1 astronomical unit, velocity down to 45 kilometers per second, the comet crossing Earth's orbital distance but far from Earth itself, geometry placing the two bodies on opposite sides of the Sun or separated by tens of degrees in their respective orbits. A month after perihelion, perhaps one. 5 astronomical units, velocity around 40 kilometers per second. The comet passing the inner edge of the asteroid belt, regions where Mars orbits and where spacecraft to the outer planets typically accelerate outward, only took a month to travel from perihelion halfway back to Jupiter's distance. The immense speed accumulated during infall, now carrying the comet rapidly outward, distance increasing by millions of kilometers per day. The Sun shrinking in angular size, solar flux diminishing, surface temperatures dropping as the nucleus cools and activity declines. Observations continue as long as brightness permits. Astrometric measurements track position against background stars, refining the orbital elements, improving predictions of future trajectory, quantifying the non-gravitational accelerations that perturb the path during active phases. Photometry monitors brightness, watching for unexpected changes that might indicate fragmentation or variations in activity. Spectroscopy, when possible, continues to measure gas production rates and composition, documenting how the coma evolves as distance increases and temperatures drop. Each observation adds to the data set, constraining parameters, reducing uncertainties, building a more complete picture of this visitor's properties and behavior. Only so many observations remain possible before the comet fades below detection thresholds. Magnitude 15, 16, 17. The limit depending on telescope size and integration time, on sky conditions and background brightness, on whether the comet passes through the Milky Way's star fields or through less crowded regions of the sky. The orbital energy remains constant throughout the departure, as it did during approach and perihelion passage. Total energy kinetic plus potential stays fixed at a positive value determined by the initial conditions. That positive value ensuring the trajectory remains hyperbolic. The comet never captured into a bound orbit, always retaining enough speed to escape. At perihelion, kinetic energy peaked while potential energy reached its minimum, most negative value. Now, climbing outward, kinetic energy decreases as potential energy becomes less negative, the sum unchanging. At infinite distance, potential energy will be zero and kinetic energy will equal the hyperbolic excess velocity, roughly 10 kilometers per second worth of energy per unit mass, the minimum speed the comet will carry asymptotically as the Sun's influence fades entirely. The mathematics ensures consistency, energy conserved, momentum conserved, trajectories deterministic and predictable, no violations of physical law, just gravity and inertia playing out their inevitable consequences. One detail becomes clear through repeated measurements. The outbound velocity exceeds the inbound velocity slightly, by perhaps a few hundred meters per second. The gravitational assist providing a net speed boost, even though energy is conserved. This apparent contradiction resolves through reference frames in the Sun's rest frame. Energy is indeed conserved and the comet leaves with the same speed it arrived with, but in the galactic rest frame, or the local standard of rest, the Sun's own motion contributes, and the rotation of the velocity vector during the hyperbolic encounter translates to a different speed after perihelion than before. The comet effectively steals a tiny bit of the Sun's orbital momentum around the galaxy, adding it to its own, leaving the encounter moving slightly faster relative to nearby stars than it arrived. The Sun compensates by moving slightly slower, but again, the mass ratio ensures the Sun's velocity change is utterly negligible Only took spacecraft mission designers decades ago to realize this effect could be exploited intentionally. Designing flybys to maximize velocity gain, stealing momentum from planets to accelerate probes toward distant destinations. 3i Atlas accomplishes the same thing unintentionally, its trajectory and timing purely accidental. But the physics works identically. Momentum traded, velocity boosted, the comet departing faster than it arrived, despite no energy being added from external sources, just gravitational dynamics playing out according to mathematical rules written into the structure of space-time. Months pass as the comet continues outward, crossing invisible boundaries marked only by orbital distances. 3 months after perihelion, 3i Atlas reaches perhaps 3 astronomical units from the Sun, velocity declining to 35 kilometers per second, approaching the distance where Jupiter orbits, though again the geometry keeps them separated. Jupiter travelling along its nearly circular path somewhere else in the orbital arc, while the comet passes through the same radial distance but at steep inclination, crossing through the plane of Jupiter's orbit rather than moving along it. The crossing takes only hours at these speeds, the comet transiting the ecliptic plane and continuing into southern celestial latitudes, climbing above or diving below the flattened disk where most solar system mass concentrates. 5 months after perihelion, perhaps 5 astronomical units out, velocity down to 30 kilometers per second, the comet reaching distances where Saturn resides, where sunlight takes 40 minutes to arrive, where surface temperatures on an icy body have dropped to perhaps 100 Kelvin or less, too cold for water ice to sublimate at any appreciable rate, even under direct illumination. The activity has ceased by this point, or nearly so. Water production declines exponentially with temperature, sublimation rates dropping by orders of magnitude as the nucleus cools, gas output falling from thousands of kilograms per second at perihelion to perhaps tens of kilograms per second at 3 astronomical units, to maybe nothing detectable at 5 astronomical units. Carbon monoxide, if present, might continue outgassing weakly at larger distances, its sublimation temperature low enough that even the faint solar flux beyond Jupiter can drive some activity. But carbon monoxide produces faint spectral signatures and minimal visible coma, difficult to detect unless present in high abundance, so any residual activity might go unnoticed in observations focused on brightness and position rather than detailed spectroscopy. The coma dissipates as production ceases, existing gas and dust dispersing into interplanetary space. The cloud that surrounded the nucleus for months gradually thinning, shrinking, eventually becoming indistinguishable from the background. The nucleus returns to dormancy, its surface cooled below sublimation temperatures. Ice locked solid again as during the long interstellar journey before solar encounter, brightness fades with distance, following the inverse fourth power law that governs reflected sunlight from extended objects. At 1 astronomical unit, if the comet reached magnitude 9, it would appear magnitude 13 at 2 astronomical units, 4 magnitudes fainter, corresponding to a factor of 40 in brightness. At 4 astronomical units, magnitude 17.8 magnitudes fainter than at 1 AU, a factor of 1600. Most amateur telescopes cannot detect magnitude 17 objects except under excellent conditions with long exposures. Professional telescopes can reach fainter, magnitude 19 or 20 or deeper, depending on aperture and integration time. But observing programs must prioritize targets, and fading comets compete with other science goals for limited telescope time. Only so many observations can be justified as brightness declines and the comet becomes less interesting, scientifically the most critical measurements having been completed during brighter phases. the remaining observations yielding diminishing returns, confirmations of trajectory rather than new discoveries about composition or activity. The trajectory becomes increasingly well determined as the orbital arc lengthens. Each additional observation refines the orbital elements slightly, narrowing uncertainty ellipses, improving predictions of future position. By 6 months after perihelion, the orbit is known well enough to predict the comet's location years or decades into the future, with uncertainties of perhaps a few hundred kilometers tiny compared to the distances involved, but still far too large to permit close spacecraft encounters without course corrections. The non-gravitational parameters have been fitted to the astrometric data, quantifying the thrust from outgassing, its effect on trajectory incorporated into models. The result is a mathematical description of the comet's path through space, encoded in 6 orbital elements or more if non-gravitational terms are included, numbers that summarize the object's position and velocity at a reference epoch and allow computation of its location at any past or future time. Only took a few hundred astrometric measurements spread over months to reduce uncertainty from tens of thousands of kilometers down to hundreds, the trajectory constrained by observations to precision far exceeding what human vision could ever achieve. Celestial mechanics providing predictive power that extends millennia forward and backward in time. Uranus distance approaches perhaps a year after perihelion. 19 astronomical units from the Sun, velocity around 25 kilometers per second. The comet reaches regions where sunlight takes hours to arrive, where temperatures hover around 50 Kelvin, where methane ice can be stable on airless surfaces. No spacecraft has visited this region recently. Voyager 2 passed Uranus in 1986. New Horizons crossed this distance on its way to Pluto, but these were decades ago or brief transits, not sustained presence. The comet moves through nearly empty space, the occasional asteroid or centaur occupying distant orbits elsewhere in the volume, but encounters vanishingly unlikely given the vastness of space and the brevity of transit. The Sun appears smaller now, a bright star among stars. Still the dominant light source, but no longer overwhelming. The sky dark enough that other stars become visible even with the Sun above the horizon. If the comet had an observer standing on its surface to perceive such things. Neptune distance comes perhaps 18 months after perihelion. 30 astronomical units out. Velocity down to 20 kilometers per second. The comet crossing the boundary that divides inner solar system from outer, a somewhat arbitrary distinction, but conventionally placed near Neptune's orbit. Beyond this lies the Kuiper Belt, a population of small icy bodies orbiting in a disk extending from Neptune's orbit to perhaps 50 astronomical units, remnants from solar system formation that never accreted into planets, preserved in cold storage for 4.5 billion years. The comet passes through this region over the next several years. Its trajectory inclines so steeply that it spends little time in the Kuiper Belt's densest regions, crossing quickly through the plane and continuing into high inclination space above or below the main disk. Encounters with Kuiper Belt objects remain improbable. The belt is sparse despite containing billions of objects, the typical spacing between members measuring millions of kilometers, collision cross-sections negligible on the timescales of a single passage. Observations become increasingly difficult beyond Neptune. The comet has faded to magnitude 20 or fainter, requiring the largest telescopes and longest integration times, visible only as a faint smudge or point of light against background stars. Astrometric measurements continue when possible, adding to the data archive. But the rate of observation drops perhaps 1 or 2 measurements per month rather than several per night, depending on telescope availability and observer interest. The science return from these late observations is minimal. The orbit is already well determined. Activity has ceased. Spectroscopy is impossible at such faint magnitudes. The observations serve mainly as confirmations, checking that the comet continues along its predicted path, documenting that no unexpected perturbations have occurred, maintaining a record of position versus time that future researchers might find useful for some currently unanticipated purpose. Only so much effort can be justified for observations that yield limited new information, resources finite, other targets more pressing, the comet becoming a historical object studied, characterized, now simply monitored occasionally as it fades into the outer solar system. The velocity continues decreasing, but asymptotically approaches the hyperbolic excess velocity, roughly 10 kilometers per second, that the comet will retain at infinite distance. At 30 astronomical units, the velocity has dropped to about 20 kilometers per second, still twice the asymptotic value, indicating the Sun's gravity still affects the trajectory significantly, pulling backward, decelerating the comet's outward motion. At 60 astronomical units, the velocity might be 15 kilometers per second closer to the asymptotic limit, but not yet there. At 100 astronomical units, perhaps 12 kilometers per second, the asymptote clearly visible in plots of velocity versus distance, the curve flattening as the Sun's influence weakens with increasing distance. Technically, the hyperbolic excess velocity is reached only at infinite distance, the mathematical limit of the velocity, as distance approaches infinity. Practically, the comet gets arbitrarily close to this limit as it recedes, the difference between actual velocity and asymptotic velocity shrinking exponentially with distance, becoming unmeasurably small beyond a few hundred astronomical units, only took the mathematics of limits, developed centuries ago by Newton and Leibniz, to describe this behavior precisely, to quantify how rapidly the approach to asymptotic values occurs, to show that trajectories governed by inverse square forces have well-defined escape velocities that depend on initial conditions but not on the details of the path taken. The fading continues relentlessly, brightness declining as the comet recedes, solar illumination weakening with the inverse square of distance, angular size shrinking similarly, the compound effect driving magnitude down by approximately 5 units per doubling of distance. At 40 astronomical units, perhaps 2 years after perihelion, the comet might appear magnitude 22, well beyond visual reach of most telescopes, detectable only with large apertures and long exposures that accumulate photons over many minutes. The signal competes with noise sky background from scattered starlight and zodiacal light, detector dark current and read noise, cosmic rays striking the camera during exposure. Image processing becomes critical, stacking multiple exposures to increase signal to noise, subtracting backgrounds carefully, tracking the comet's motion against background stars to prevent trailing that would smear the faint point source. Even with optimal technique, the comet becomes challenging to detect reliably. The difference between a faint comet and a noise spike, often ambiguous in single images, requiring multiple detections over multiple nights to confirm continued presence. The last reliable observations likely occur sometime between 2 and 3 years after perihelion, when the comet lies perhaps 50 or 60 astronomical units from the Sun, faded to magnitude 23 or 24. A few final astrometric measurements pin down position, confirming the trajectory remains consistent with predictions, documenting that the comet still exists as a detectable object at these vast distances. Then the observations cease, not because the comet has disappeared, but because it has become too faint to observe economically. The telescope time required to detect it no longer justified by the minimal scientific return. The comet continues outward, invisible now to ground-based instruments, perhaps detectable with space telescopes like Hubble or James Webb if pointed precisely at its predicted location with long integrations. But such observations would require substantial resources for uncertain gain. More likely, the comet simply fades from human awareness, its position known mathematically from orbital calculations but unverified by actual detection, continuing its journey whether watched or not. One detail marks the end of the observational campaign, the final ephemeris, a table of predicted positions extending years or decades into the future, calculated from the best-fit orbit determined from all available astrometry. The ephemeris lists right ascension and declination at regular intervals, perhaps one entry per month, or per year for distant dates, coordinates that specify where the comet should appear on the sky as seen from Earth or from the solar system barycenter. Uncertainties grow with time extrapolated from the last observation, position errors accumulating as the comet moves through space, small errors in velocity translating to larger and larger position, uncertainties the farther one projects into the future. By a decade after last observation, the comet's position might be uncertain by thousands of kilometers. By a century, perhaps hundreds of thousands of kilometers. By a millennium, the uncertainty could span millions of kilometers. The comet's location known only to within a volume of space comparable to the distance between planets. Still, the trajectory is known far better than if no observations had ever been made. The mathematics capturing the comet's motion with precision impossible through casual observation, the crossing of the heliopause. The boundary where solar wind yields to interstellar medium occurs at roughly 100 astronomical units, give or take several tens of AU depending on direction and solar activity. Voyager 1 crossed the heliopause at approximately 122 AU in 2012, entering interstellar space officially. Though still within the Sun's gravitational influence, still technically orbiting the Sun on a hyperbolic escape trajectory similar to 3I Atlas. The heliopause is not a sharp boundary, but a transition region where solar wind pressure balances interstellar plasma pressure, where the magnetic field transitions from solar-dominated to galactic-dominated, where particle populations shift from solar energetic particles to galactic cosmic rays. For 3I Atlas, this crossing will occur perhaps 5 or 10 years after perihelion, depending on exact velocity and direction. The comet passing from the heliosphere, the bubble of solar influence, into the local interstellar medium, joining the vast population of matter drifting between stars. Beyond the heliopause, the solar system's influence persists through gravity alone. The Sun's gravitational reach extends far beyond the heliopause, technically to infinite distance, though weakening with distance, becoming negligible compared to other forces at distances measured in light years. The Oort cloud, a hypothetical spherical shell of comets surrounding the Sun, extends perhaps 50,000 astronomical units, nearly a light year, its outer edge defining the practical boundary of solar gravitational dominance, the region where passing stars can perturb orbits more strongly than the Sun can hold them. 3I Atlas will cross through the Oort cloud region over the next several thousand years, moving outward at roughly 10 kilometers per second, covering an astronomical unit every few days, a light year every 60,000 years. During this transit, the comet will pass perhaps a few billion kilometers from the nearest Oort cloud objects close on interstellar scales, but vast compared to object sizes. Encounters between 3I Atlas and native solar system comets, vanishingly improbable. The trajectory in interstellar space becomes a straight line to excellent approximation. gravitational perturbations from nearby stars remain negligible over timescales of thousands of years. Typical stellar densities in the solar neighborhood amount to perhaps 1 star per 10 cubic parsecs. Separations of several light years. Gravitational forces at these distances utterly insignificant. The sun's own gravity, falling off as inverse distance squared, contributes less than a millimeter per second squared of acceleration at 1 light-year distance, sufficient to keep Oort cloud comets barely bound, but insufficient to curve hyperbolic trajectories noticeably. 3I Atlas coasts on momentum, velocity effectively constant at 10 kilometers per second relative to the Sun, trajectory pointing toward coordinates in the southern sky. Crossing the distance from Sun to Alpha Centauri, 4 light-years in roughly 120,000 years at this speed, only took a few months of gravitational interaction with the Sun to set this trajectory. To add the velocity boost that distinguishes the outbound path from the inbound path, and now decades and centuries and millennia of coasting follow, the comet moving ballistically through the near vacuum of interstellar space. One mystery persists into this distant future, the comet's fate over mega-year timescales. Galactic dynamics eventually dominate encounters with molecular clouds, passages near other stars, the overall gravitational potential of the Milky Way's disk and halo. Each of these effects is tiny on timescales of thousands of years but accumulates over millions. A passing star at a distance of 1 light-year can perturb the trajectory by kilometers per second, adding or subtracting velocity, altering direction, possibly even capturing the comet into orbit around the star if the geometry and timing allow. Though capture probabilities are low, molecular clouds, dense regions of gas and dust where stars form, exert tidal forces that can strip comets from stellar systems or perturb trajectories significantly. The Milky Way's gravitational field steers all objects in the galactic disk, imposing an acceleration of roughly 10 meters per second, squared perpendicular to the disk, sufficient to oscillate objects through the disk on timescales of tens of millions of years. Over 1 billion years, 3I Atlas will likely have encountered several stars, crossed through the galactic plane multiple times, possibly been captured temporarily by another system before being ejected again, its trajectory written and rewritten by gravitational interactions too complex to predict in detail from current observations. The final velocity, 10 kilometers per second relative to the Sun, translates to perhaps 20 or 30 kilometers per second relative to the local standard of rest, depending on exactly how the Sun's motion combines with the comet's departure direction. This speed is typical for stars in the solar neighborhood, all moving with velocities of tens of kilometers per second relative to the galactic average, each on its own orbit around the galactic center, completing one circuit every few 100 million years. 3I Atlas joins this population, no longer distinctively interstellar but simply one object among countless others drifting through the galaxy, indistinguishable from any other small body ejected from any other planetary system. Its brief encounter with our solar system, a transient episode in a journey that has lasted millions of years and will last millions more, unobserved, uncharted, known only through mathematical projections that grow increasingly uncertain with time, the comet fading from record as it faded from view, continuing nonetheless, following the trajectory imprinted during perihelion passage, bound for no particular destination, aimed at no particular star, simply moving through the galaxy as it has always moved, as it will move until some future gravitational encounter alters its path or sends it spiraling into a star or planet, an ending measured in millions or billions of years, far beyond any predictive capability of current observations, deep into the uncertain future, where only statistical expectations replace specific predictions. The trajectory extends into the interstellar medium, a path traced through space that will carry 3I Atlas past no particular landmark for tens of thousands of years. The direction aims generally toward coordinates in the southern celestial sphere, vaguely in the direction of Centaurus or Vela, though these are human designations imposed on a sky that appears different from every vantage point. Constellations dissolving into arbitrary patterns when viewed from distances of light years. No bright star lies directly along the trajectory. Alpha Centauri sits several degrees away in angular terms, a separation that translates to light years of lateral distance at interstellar ranges. Canopus, brilliant in Earth's southern sky, lies in a different direction entirely. The comet heads into relatively empty space, a region between stellar neighborhoods where only faint red dwarfs and brown dwarfs populate the volume, objects too dim to have received names or catalog numbers unless specifically surveyed by infrared missions designed to find such dim bodies. The velocity of 10 kilometers per second, maintained approximately constant now that solar gravity has become negligible, amounts to about 30,000 kilometers per hour, or roughly 7 million kilometers per day, or 2.5 billion kilometers per year distances that dwarf planetary orbits but remain tiny compared to interstellar separations. 1 light year equals roughly 9.5 trillion kilometers, requiring nearly 4,000 years to traverse at this speed. The nearest stars to the Sun, the Alpha Centauri system at 437 light-years, Barnard's star at 6 light-years. Various others within 10 light-years will not be approached by 3I Atlas unless its trajectory happens to aim toward one of them, which seems unlikely given the random nature of its departure angle. More probable is passage through empty regions where stellar densities are typical of the galactic disk. 1 star per few cubic parsecs distances between neighbors measured in multiple light years. The comet crossing these gulfs over tens of thousands of years, moving through darkness punctuated occasionally by distant stars that grow slowly brighter over millennia, then fade again as the comet passes. The interstellar medium itself offers little resistance. Gas densities in the local bubble a region of hot, low-density plasma surrounding the Sun, inflated by ancient supernova explosions, average perhaps 0.1 atoms per cubic centimeter, mostly hydrogen, with traces of helium and heavier elements. At 10 kilometers per second, the comet sweeps through this gas at a rate determined by its cross-sectional area, perhaps 1 square kilometer, if the nucleus is 1 kilometer across. The mass flux intercepted amounts to roughly 10 dose 16 kilograms per second, utterly negligible. The comet losing more mass to sporadic outgassing of trapped volatiles or erosion by cosmic rays and interstellar ultraviolet than it gains from sweeping up interstellar hydrogen. Drag force from this tenuous medium is unmeasurably small, perhaps 10, 15 newtons, incapable of altering the trajectory detectably over millions of years. Only took spacecraft crossing through the heliopause to measure these interstellar densities directly. Voyager 1 and 2, detecting plasma oscillations and particle populations characteristic of the local interstellar medium, confirming theoretical predictions about conditions in the space between stars. Radiation continues to affect the comet's surface despite vast distance from any star. Galactic cosmic rays, high-energy particles, mostly protons and heavier nuclei accelerated by supernova shocks, and other violent astrophysical processes permeate interstellar space, bombarding all surfaces with ionizing radiation. The flux is modest, perhaps a few particles per square centimeter per second, but the energies are high, hundreds of MeV to GeV, sufficient to penetrate meters into solid material, gradually damaging crystal structures, breaking chemical bonds, inducing nuclear reactions that transmute elements slowly over millions of years. Surface ice, if any, remains exposed. undergoes radiolysis radiation-driven chemistry that breaks molecules apart and allows them to recombine into new compounds. Complex organic molecules form through these processes, simple ices like water and methane, and carbon dioxide slowly polymerizing into long-chain hydrocarbons and nitrogen-bearing compounds. The same chemistry that darkens comet surfaces and produces the organic rich crusts observed on nuclei visited by spacecraft. The rate is slow, perhaps a millimeter of surface modified per million years, but integrated over the age of the solar system. Substantial mantles can develop, layers of radiation-processed material coating primordial ice, insulating the interior and altering surface properties. Temperature equilibrates to the cosmic microwave background plus contributions from starlight and cosmic rays. The CMB, relic radiation from the Big Bang, fills all of space with a black body spectrum corresponding to 273 Kelvin, providing a minimum temperature floor for any object not heated by other sources. Starlight adds a small contribution. The integrated flux from all stars in the galaxy amounts to roughly equivalent to one star seen from a distance of several light years, raising equilibrium temperature by perhaps a few Kelvin. Cosmic ray impacts deposit energy sporadically, heating surfaces microscopically at impact sites, but averaged over time and area the contribution is minor. The result is a nucleus surface at perhaps 3 to 5 Kelvin, cold enough that all common volatiles remain frozen water ice, carbon dioxide, carbon monoxide, methane, nitrogen, all stable as solids at these temperatures. Only hydrogen and helium remain gaseous, but these are too volatile to have been retained in the nucleus during formation, escaping to space long ago. The comet becomes a frozen artifact, its chemistry arrested, composition preserved in deep cold until the next stellar encounter, which might not occur for millions of years. One detail emerges from considering the journey duration at 10 kilometers per second. 3I Atlas will travel 1 parsec, roughly 3.26 light-years, in about 30,000 years. The galactic disk has a scale height of a few hundred parsecs, a diameter of roughly 30,000 parsecs. Crossing from one side of the galaxy to the other at this speed would require hundreds of millions of years, timescales comparable to the age of the oldest stars, to the formation epoch of the galactic disk itself. But the comet does not move in a straight line relative to the galaxy. It orbits the galactic center like everything else in the disk, completing one orbit every few 100 million years, though its orbit differs from the Sun's now, altered by the Perihelion passage. The relative motion between 3I Atlas and nearby stars amounts to perhaps 20 or 30 kilometers per second, typical stellar peculiar velocities, so from the perspective of the local stellar population, the comet moves at unremarkable speed. Just another object drifting through the neighborhood. No more notable than the billions of other comets ejected from billions of other planetary systems over the galaxy's lifetime. The trajectory will curve gradually under the galaxy's gravitational field. The overall potential imposed by hundreds of billions of stars and vast amounts of dark matter distributed through halo and disk. This curvature is gentle accelerations of order 10 meters per second, squared perpendicular to the galactic plane, sufficient to produce oscillations through the disk with periods of tens of millions of years, but insufficient to bend the trajectory noticeably over thousands of years. The comet will likely cross the galactic plane multiple times over the next 100 million years, each crossing carrying it through the denser regions of the disk, where molecular clouds and stellar clusters concentrate, where gravitational perturbations become more frequent, where the probability of stellar encounters increases. Between crossings, it will spend time in the galactic halo, regions above and below the disk where stellar densities are lower, and matter consists mostly of dark matter and hot gas, where perturbations are rare and trajectories remain nearly straight for millions of years at a stretch. Only took decades of galactic dynamic studies to map out these oscillations, to understand how objects move through the disk under the combined influence of local stellar masses and the overall gravitational potential, to calculate typical encounter rates and perturbation magnitudes for objects drifting through interstellar space. The probability of stellar encounter can be estimated crudely. Stellar densities in the galactic disk average perhaps 0.1 stars per cubic parsec. The comet has an effective cross-section for significant gravitational perturbation. Perhaps encounters within 1 parsec produce velocity, changes of order kilometers per second. The cross-sectional area amounts to roughly 10 square parsecs. The volume swept per unit time equals this area times velocity, giving perhaps 3 cubic parsecs per million years. Multiplying by stellar density suggests one significant encounter every few million years on average. Though this is order of magnitude reasoning with large uncertainties, some encounters will be distant and produce minimal perturbation. Others will be close passing within a fraction of a light year and alter the trajectory dramatically, adding or subtracting kilometers per second of velocity, redirecting the comet toward new regions of the galaxy over billions of years. The accumulated effect of many encounters randomizes the trajectory completely, the comet's motion becoming a random walk through the galaxy, any memory of the original ejection direction from its parent system erased by countless gravitational interactions. The destination, if it can be called that, remains undefined. No specific endpoint exists. No place the comet is aimed toward. No star it will necessarily encounter. The trajectory is simply a direction in space, maintained approximately until some future perturbation changes it, then maintained in a new direction until the next perturbation, and so on. The path through the galaxy determined by the history of gravitational encounters, a stochastic process without deterministic outcome, perhaps in a few million years. 3I Atlas will pass close to a star with its own planetary system, falling into that system's gravity well, possibly captured into an elliptical orbit, possibly passing through on another hyperbola, briefly warming in the light of a different sun before continuing outward. Perhaps it will collide with a planet or moon impacting at tens of kilometers per second, vaporizing on contact, delivering ice and organics from one stellar system to another, a microscopic contribution to panspermia or volatile delivery, but a contribution nonetheless. Perhaps it will drift for billions of years without significant encounter, gradually crossing the galaxy, eventually lost to observation, position unknown, fate uncertain, existing only as mathematical abstraction, a trajectory calculated once and never verified again, predictions extending into a future too distant to confirm or refute, the comet continuing its journey in darkness, unseen and unrecorded, a small piece of ice carrying chemistry forged in some ancient protoplanetary disk, wandering forever through the vast spaces between stars. A few particles remain behind, scattered along the trajectory during the months of activity. Small fragments of 3I Atlas left drifting in the inner solar system. Dust grains, released during perihelion passage, follow their own orbits, now each grain a separate object moving under solar gravity and radiation pressure, perturbed by the Poynting-Robertson effect that causes slow orbital decay. The smallest grains, micron-sized or smaller, experienced strong radiation pressure at release, accelerated anti-sunward into trajectories quite different from the parent comet's path. Some were pushed outward entirely, achieving escape velocity through photon momentum alone. Tiny particles carried by light into interstellar space on paths diverging from the nucleus. Others fell into elliptical orbits, spiraling slowly sunward under pointing Robertson drag, taking thousands or millions of years to complete the inward migration, eventually vaporizing when they approached too close to the sun's heat or colliding with planets or moons during their long decay. The larger particles, millimeter to centimeter scale, remain closer to the original trajectory, their greater inertia making them less susceptible to radiation forces. These particles orbit the Sun on hyperbolic or highly elliptical paths similar to the comets spread along the arc traced during perihelion passage, forming a tenuous meteoroid stream that extends from perhaps half an astronomical unit out to several AU. The distribution density highest near perihelion, where outgassing was strongest, declining with distance as activity decreased. The total mass in this stream amounts to perhaps thousands of kilograms, a small fraction of the total mass lost during activity, most of which consisted of gas that dispersed into interplanetary space and cannot be recovered, distributed over millions of cubic kilometers. Average densities far too low to constitute collision hazard, but sufficient that sensitive instruments might detect occasional impacts. Earth's orbit does not intersect this debris stream. The geometry prevents it. The comet's perihelion at 0.47 AU places it inside Earth's orbit, while the steep inclination carries the trajectory through the ecliptic plane at angles that miss Earth's path by millions of kilometers. No meteor shower will result from 3I Atlas. No annual display of shooting stars when Earth crosses the stream. No connection between this interstellar visitor and the night sky phenomena familiar to observers watching Perseids or Leonids or other established showers. The particles will orbit for centuries or millennia without human observation, invisible unless spacecraft happen to pass nearby and detect impacts on their instruments, gradually dispersing through orbital evolution and radiation effects until the stream becomes too diffuse to recognize as coherent structure. Individual grains lost among the background population of interplanetary dust that fills the solar system from sources both cometary and asteroidal. Some particles may eventually reach Earth despite the orbital mismatch, redistributed by gravitational perturbations over long timescales. Planetary encounters can alter particle orbits significantly, Jupiter especially, with its massive gravity and position in the outer solar system, where many particles pass during their perihelion cycles. A grain initially on a hyperbolic trajectory might be perturbed into an elliptical orbit by a distant Jupiter encounter, the new orbit precessing slowly under planetary perturbations, eventually intersecting Earth's path centuries or millennia after the original ejection. The probability for any individual grain is low, but considering the thousands of particles in the stream, perhaps a few dozen will eventually collide with Earth, entering the atmosphere at tens of kilometers per second, vaporizing from friction, producing brief streaks of light visible to any observer who happens to be watching the right patch of sky at the right moment. These meteors will arrive individually, randomly distributed in time, not concentrated into showers, indistinguishable from sporadic meteors that occur constantly from various sources throughout the year. The particles carry information about the comet's composition, frozen samples of nucleus material ejected during activity and preserved in the cold of space. Dust composition reflects the minerals and organics present in the nucleus silicate grains typical of rocky material, perhaps olivine and pyroxene and other common minerals, mixed with organic compounds ranging from simple hydrocarbons to complex macromolecules. If analyzed in a laboratory, these grains would reveal isotopic ratios, diagnostic of formation conditions, the deuterium to hydrogen ratio in water, the carbon-13 abundance, the nitrogen-15 fraction, all telling stories about the chemistry of the protoplanetary disk where the comet formed billions of years ago around some other star. But the grains will likely never be collected or analyzed. They are too small. too dispersed, their orbits too poorly known to permit targeted collection, and most will burn up in Earth's atmosphere if they ever arrive. Their information converted to heat and light and ionization in the upper atmosphere, detected perhaps as meteors but not recovered as physical samples. One detail persists in the scattered particles they represent, the only physical samples from another stellar system's planetary formation process accessible in our solar system. Beyond the 3 interstellar objects detected so far, meteorites collected on Earth originate from asteroids and comets within our solar system, fragments of bodies that formed here 4.5 billion years ago. Presolar grains, tiny inclusions found in some meteorites, formed before the Sun existed, represent matter from other stars, but not from planetary systems. Instead, coming from stellar outflows and supernova ejecta, processed through star interiors rather than protoplanetary disks. The dust from 3I Atlas, if it could be collected, would offer direct comparison between our solar system's composition and another system's, testing whether planet formation chemistry is universal or varies between stellar environments, whether the isotopic ratios and mineral assemblages found in solar system materials represent galactic averages or local peculiarities. Only took 3 interstellar visitors to make such samples theoretically accessible, though practically unreachable given current technology and the enormous challenge of locating and collecting microscopic grains drifting through interplanetary space along poorly constrained orbits. The gas released during activity has dispersed more completely than the dust, molecules and atoms spreading into interplanetary space at thermal velocities, colliding occasionally with solar wind particles, gradually ionized by solar ultraviolet. The ions swept away by magnetic fields while neutral atoms continue drifting outward. Water molecules photodissociate into hydrogen and oxygen within hours of release, the hydrogen atoms forming a vast cloud that streams anti-sunward, the oxygen atoms scattering more slowly, eventually lost among the background population of interplanetary neutrals. Carbon-bearing molecules, carbon monoxide, carbon dioxide, methane, organic compounds undergo similar fates, broken apart by sunlight, their constituent atoms dispersing, the carbon eventually incorporated into dust grains or ionized and carried away by solar wind. The molecules from 3I Atlas mix with molecules from other sources, solar wind particles, Earth's escaping atmosphere, gas from solar system comets, ions from the outer planet's magnetospheres becoming indistinguishable from the general interplanetary medium within weeks or months of release, their interstellar origin erased, their chemistry homogenized with solar system material. A few molecules might survive longer in the cold outer solar system, beyond the reach of intense solar ultraviolet, drifting outward at thermal velocities for months or years, before photoionization or collisional ionization removes them. These molecules carry isotopic signatures of their origin, deuterium and carbon-13 and nitrogen-15 ratios potentially different from solar system values. But detecting and measuring them requires spacecraft positioned in the outer solar system with mass spectrometers sensitive enough to distinguish trace species against background noise. No such spacecraft currently operate in suitable locations with appropriate instruments, so the isotopic information disperses unmeasured, molecules eventually ionized or condensing onto dust grains, their information content degraded by mixing and chemical processing, the opportunity to sample interstellar material lost to time and diffusion. The wake of 3I Atlas, the volume of space traversed during its months in the inner solar system, retains traces of the visit for years. Dust particles orbit near the original trajectory, slowly dispersing through gravitational perturbations and radiation effects. Neutral gas atoms continue outward at thermal velocities, gradually spreading into a diffuse cloud that overlaps other sources and becomes unidentifiable as a distinct population. Ions, swept away by solar wind, carry momentum and energy into the distant reaches of the heliosphere, eventually mixing with the general plasma population at the heliopause and beyond. Each component leaves a signature, temporarily, but the signatures fade, dust orbits evolving until they no longer cluster near the original path, gas atoms dispersing until their density becomes unmeasurable above background, ions recombining or escaping to interstellar space. Within decades, the solar system will show no evidence of the passage except in databases and scientific publications, orbital elements recorded in catalogues, spectra archived on servers, images preserved in digital formats. The physical traces vanish, but the information persists, encoded in human records. A small addition to the accumulated knowledge about interstellar objects and comet behavior and the diversity of material drifting through the galaxy. Only took a few months of activity to create these traces, and only a few decades for them to disperse beyond recognition. The comet's brief contribution to the inner solar system's matter budget fading into the general background, indistinguishable from the countless other sources that have deposited similar material over billions of years. The solar system erasing evidence of the visit as efficiently as it erases all transient phenomena, returning to equilibrium that acknowledges no particular visitor, no special event, just continuous slow cycling of matter through interplanetary space on timescales measured in thousands and millions of years. The mathematics continue. Equations describing motion through space that no longer requires observation to verify. Position as a function of time. Velocity as a function of distance. Trajectory plotted through coordinates that span parsecs and centuries. All encoded in orbital elements determined months or years ago from astrometric measurements that have long since ceased. The numbers persist in databases: eccentricity, perihelion distance, inclination, argument of perihelion, longitude of ascending node, time of perihelion passage, 6 values that summarize the entire trajectory, past and future, reducing the comet's journey to algebra, to mathematical objects that obey differential equations written centuries ago by minds that never imagined interstellar visitors, but understood gravity well enough that their equations apply regardless. The comet itself moves beyond the heliopause now, or will soon, crossing from heliosphere into interstellar medium, a transition it cannot perceive, no discontinuity in the vacuum it travels through, merely a change in plasma density and magnetic field topology, subtle shifts in particle populations, the solar wind fading to background while galactic cosmic rays dominate. Temperature remains constant at a few Kelvin, radiation environment changes only marginally. The nucleus continuing its existence in frozen silence, surface unchanged since activity ceased years ago. Ice locked beneath radiation-processed crust. Interior preserving chemistry from formation epoch. Billions of years old. Older than Earth's oceans. Older than the Moon. Perhaps older than the solar system itself if the comet formed early in its parent system's history. Velocity holds steady near 10 kilometers per second. The asymptotic value reached as solar gravity weakened to negligibility, maintained now through inertia alone. Newton's first law in its purest form: objects in motion remain in motion unless acted upon. And here, no forces act with sufficient strength to alter the trajectory detectably. The comet coasting through near-perfect vacuum, following geodesics through space-time that appear as straight lines to excellent approximation, curving only imperceptibly under the galaxy's overall potential, moving as it has moved for millennia before solar encounter, as it will move for millennia after, unchanged, persistent, a fragment of ice carrying memory of another star's planetary disk into the vast spaces between stars. Distance increases without pause. 100 astronomical units. 200. Eventually thousands. The numbers growing steadily, though no longer measured. No telescopes tracking position. No astrometric observations refining the orbit. Just mathematical extrapolation from final measurements. Predictions that grow less certain with each passing year as unmodelled perturbations accumulate tiny gravitational tugs from distant Kuiper belt objects, subtle radiation forces from starlight, possible outgassing from residual volatiles, all contributing errors that compound over time. Position uncertainty expanding into volumes that eventually encompass cubic light-years. The comet's location known only statistically, probably within some region of space, but not precisely where. The stars shift slowly in apparent position as the comet moves, parallax accumulating over decades and centuries, nearby stars drifting across the sky relative to distant background, constellations distorting as perspective changes, the familiar patterns visible from Earth dissolving into new arrangements, arbitrary groupings that would mean nothing to human observers, celestial cartography rewritten by motion through three-dimensional space, the sky transforming gradually, imperceptibly on human timescales, but dramatically over thousands of years. Orion's belt spreading, the Big Dipper warping, Crux rotating, all the navigational stars of human history sliding into new configurations, unrecognizable, unfamiliar. The sky, as seen from 3i Atlas, becoming progressively more alien, disconnected from Earth's vantage, a view unique to this particular trajectory through this particular volume of the galaxy. Silence surrounds the comet, not the silence of absence, but the silence of vacuum. Space that cannot carry sound because sound requires medium, requires atoms close enough to collide and propagate pressure waves. And here atoms are separated by meters or kilometers, collisions rare, no medium, no sound, just electromagnetic radiation crossing the void at light speed, photons from distant stars arriving after journeys of years or centuries, cosmic microwave background photons traveling since the universe was 300,000 years old, neutrinos from the sun passing through the comet without interaction, all of it silent, intangible, the comet existing in a realm where human senses would perceive nothing, no light bright enough to see without instruments, no warmth, no pressure, no indication of motion except through careful measurement of stellar positions over long intervals. Time passes without marking. No seasons here, no day-night cycle except the rotation of the nucleus itself. Period unknown, spinning in darkness, one face then another, presented to the faint starlight, temperature uniform within fractions of a Kelvin, no thermal gradients to speak of, no activity, no change, just existence in the present tense continuous, the comet being rather than becoming, state stable, composition fixed, motion uniform. Everything that can reach equilibrium has reached it. Everything else proceeds too slowly to measure cosmic ray damage accumulating atom by atom. Micrometeor impacts rare and random, perhaps one per century, perhaps fewer. Each event insignificant against the nucleus mass. Erosion occurring but imperceptibly. The comet essentially unchanged over timescales of human lifetimes or civilizations, requiring millions of years for substantial alteration. Deep time operating at its characteristic pace. Patient, inexorable, indifferent. The journey continues into futures too distant to imagine concretely. 10,000 years from now, the comet will be several light years from the sun, still moving at 10 kilometers per second, perhaps perturbed slightly by then, trajectory altered by encounters not yet occurred, position shifted by gravitational interactions still in the future, unpredictable in detail, but statistically characterizable, likely still in the general direction it departed toward. Probably not captured by any star. Possibly passed close to something, but probably not. Most of interstellar space being empty. Encounters being the exception rather than the rule. 100,000 years from now. Tens of light years distant, moving through regions of the galaxy unvisited by anything from our solar system except other ejected comets and the Voyager spacecraft. All of them spreading slowly through the galactic disk. Ambassadors unintentional and unaware, carrying atoms forged in the sun or in older stars, dispersing solar system material atom by atom into the interstellar medium through impacts and radiation sputtering, contributing negligibly to galactic chemistry, but contributing nonetheless. Million-year futures see the comet crossing substantial fractions of the distance between spiral arms, moving through the galaxy's structure, crossing molecular clouds perhaps, encountering stellar nurseries where new stars form, passing through H2 regions ionized by massive young stars, witnessing supernovae from safe distances measured in parsecs, all of it drifting past in slow motion. Events separated by thousands of years of travel, the comet threading through cosmic geography on a path determined by gravitational interactions, too complex to predict but too weak to stop. Momentum carrying it forward regardless. The trajectory, a random walk through the galaxy's potential well, destination uncertain, outcome undefined, ending unknown and perhaps irrelevant, the journey itself being the only certainty, motion through space continuing as long as space exists to move through, until entropy and expansion and the ultimate fate of the universe become relevant on timescales measured in billions of years. Deep time beyond human comprehension. Futures where predictions lose all meaning and only the most general thermodynamic principles remain valid. The equations do not care whether anyone solves them. The orbit persists whether calculated or not. The comet moves whether observed or not. Mathematics describes but does not determine, captures patterns in symbols, but changes nothing about the motion itself, the trajectory existing independent of human awareness, following physical law that operated before humans existed and will operate after humans are gone. Gravity and inertia and momentum conservation written into space-time structure, playing out their consequences in darkness, in silence, in the endless reaches between stars where 3i Atlas continues its journey. Small piece of ice from somewhere else, passing through our neighborhood briefly, departing now into distances too vast for recovery or visitation, going wherever momentum and gravity take it, unreachable, unknowable beyond what brief observations revealed, fading from human knowledge, but not from existence, still there, still moving, still real, somewhere in the dark between stars, travelling, always travelling, the journey without end extending forward into time, too deep to measure, the comet and its trajectory and the mathematics that describe both persisting in their separate ways, one physical and one abstract, but both real, both continuing, both describing the same motion through the same space, the same endless falling through gravity wells that never quite capture, the same escape that never quite completes, asymptotic approach to conditions at infinity, the mathematics and the motion both approaching limits they will never quite reach, continuing, persisting, existing, moving through the dark,